for the work in the field. Unsatisfactory, poor, satisfactory, good, excellent.
I don't
Mastery, understanding of physics. You just put access there. This is quick. It's like a form that teacher was supposed to fill out. Just it's the questions how good are you using access. It's a new standard. I mean, I can fill it out for you.
What goes around comes around.
Morgan. Yes.
I think you're. She said Morgan.
Morgan. He's a PK student.
If you want to discuss it any further, I'll be happy to. Because I'm an advocate of those models. I know the history of CFAX. It was made on the back of an optic model.
I want a goodie. I want a goodie. What? This. Yeah. No, yeah. I took it up in the quality of this, but I don't know.
I know.
If you look at the other one, you'll find everything is right. I don't necessarily want to talk about it. We can use it with and I can show you. This is a paper we wrote a long time. Just email it.
Fanciest defensive ever.
I'll send you that paper and you can see the line.
Okay. Thank you.
I'll go. I'm gonna go get my glasses. No, I'm gonna go get my glasses. This is not what we signed off, right?
No, this is like evaluation where you put marks and stuff better.
Just do it like afterwards.
Yeah.
And then where do I?
You don't sign it at all.
Give it to them.
You just give it to me.
Okay.
I mean, yeah.
Oh, that's only for professors. They didn't even stop.
Okay. Do we know where the rest of the committee is?
But to kill time, I can light that up and then wait for that.
Sure.
For like 4 years, I wanted to light a pie on fire to start my defense, and I'm going to do that.
I think there was a chemistry experiment like this in Virginia in a high school.
We did it the night before that they messed up. We actually did it successfully. No one got hurt. So,
You caramelizing the.
there's an apricot glaze there, yeah. So see how that goes.
Is that Sambuca?
It's a single malt that a friend got me 5 years ago.
Single.
No,
malt.
my hands are awfully shaky, and this is annoying.
Single malt will. I don't think that will like.
It will. I tested it this morning, but I may need to soak this a bit more because I made the pie 4 days ago.
Oh, this is really.
Just pour it freely over the
Yeah,
flame.
but then it's
That's what we always do.
No, if you had
Pour
Sambuca,
gasoline
it'd be no
on
problem.
the barbecue.
Right?
Well, it's a mist system, is what we say. We can just keep sitting here. And
I know love from this. Oh, I'm so disappointed.
Just leave the match there.
That was your experiment?
That's it.
No,
You missed the whole thing.
it's not across the whole.
Where are the lasers? Oh, that's.
He proved that if you spill enough on the desk, it'll ignite the desk tip.
My hands are
You're
too
gonna do a high
shaky, so
school
I'm not going to do this
experiment.
one. I did that last night. They did tornadoes and like hovering premix flames. So that could have been better, but whatever. Adequate.
All right, we're missing two more committee members. Yes.
Should we get a gas lighter?
So it's still going, just be aware that it's still going.
Big tool could be for the students too. It was a joke.
All right, yes, Mike, this is, I think we're supposed to fill it out at the end. And I can fill it out for you if you like, but.
Mike,
All right.
very distinguished.
One of these for the whole thing.
We're not
Very
really,
distinguished.
only one? You sure? Because,
One's fine.
all right, so you misinformed me, apparently only one.
Yeah, we only need
Even
one.
I just got it. That's great. That's less work for you guys.
Okay, one it is, that has to be discussed.
Yeah.
All right, Michael? Right, Michael.
How's everybody's day going?
Great.
Day's about to get a lot harder. The easiest part.
All right, I think Michael is coming. We're going to start without him.
Is he on the committee?
Yes, he is, but he is just, drifting towards that place. He's very close. So today we're going to hear defense by Isaac Leventon. Isaac has been my student for 5 years. He did his master's in fire protection engineering department and his PhD in mechanical engineering. I think he did a lot of very solid work. I think he will probably have an opportunity to present on the fraction of it here, and you will have an opportunity to see how good work is. Besides the fact that I think he did a very solid research, I want to point out that Isaac has introduced two significant initiatives in the department. One of them was associated with the fact that he has a great passion for teaching, and to realize this passion, he started an outreach program here that consisted of a class for the local high school kids, where he got them together once a week and used the ideal and principles of fire dynamics to educate them on the subject of math, chemistry, and physics. That program has been running by Isaac for 2 years and been very, very successful, and we hope to continue doing it after his departure. Now, the last point that I'd like to make is that I think all of us here, we know that Isaac injected life in this department, both literally and figuratively, right? The turtles that we have outside, the fish, it's all due to him, and the figurative part will be missing a lot. Thank you very much, and go ahead and do your presentation.
Thank you. That was really nice. Thank you. So after 5 years, I'm finally here to defend my dissertation, which we titled Prediction of Upward Plane Spread Over Polymers. And I want to start by just laying the foundation for why all of this matters. And we're going to focus in on plane spread because in the early stages of fire, this is really what's controlling the early stages of fire growth. So if we want to know how something is going to go from a small fire that we're not too concerned about to something much more larger and dangerous, then we need to understand flame spread. We're specifically focusing in on upward flame spread because in this direction it's fastest and thus most hazardous. And a lot of our work has gone into taking detailed measurements of flame to surface heat feedback because that's really what's controlling material burning rate in this system. So this has been a problem that we've known about for decades. So there's a wide range of test standards out there that are meant to assess material performability in this way. Unfortunately, they show little ability to actually predict material performance outside of standard test conditions. Usually you're going to get some sort of qualitative ranking, so pass fail or a 0 to 100 score, and that's supposed to tell you all you need to know about your material. And it's difficult because you'll often see conflicting assessments between these different tests, and it's difficult to actually interpret for how well your material is going to perform in your conditions. I want to bring up, I guess, why we're focusing on plastics specifically. We're starting to see that with the push for lighter and cheaper and more energy efficient materials, plastics are being used in a wide range of environments and applications that they just weren't used in before. If you can think about the last time you were on a plane, and the floor coverings and the walls and the windows and the seats that you're sitting on, the cabinets, pretty much everything is lined with some kind of plastic. So we definitely want to understand how those materials are going to behave in a fire scenario. And one point that Stas brought up a couple of days ago was the idea of moving into tiny houses. So the Plastics Makes It Possible Foundation is touting all the wonderful things that can come from using plastics all around you. So the movement for these tiny homes is have this nice small footprint where you're living. It's better for the world, it's better for the environment. So they're advertising and promoting this 170 square foot home, pack everything you have inside of there. It's all made from wood, and they're going to wrap it entirely in plastic. So there's polystyrene in the floors. It's entirely wrapped in vinyl. The windows are vinyl. They have polycarbonate sunroofs. And in between every crack in the wood, they've loaded that with polyurethane foam. So trust us, it's great. It's energy efficient. Live inside here, and it's going to be fine. All of those things, unfortunately, burn. We want to understand how they do, so we can help them make them safe. So that's our problem. Let's take a look at the actual system that we're trying to understand better. So we're looking at wall flame spread. On the right side here, we're going to have our material that's burning. On the left is the flame that's heating it up. And in a really simple way, we can just treat this as heat up your material. It's going to degrade. It produces flammable vapors. When those mix with the ambient oxidizer and air, that can burn, send energy in all different directions. Some of that goes back into the material itself, causing further heating and further degradation, and the process continues. So we want to understand this positive feedback cycle better. A couple of the, parameters here that I want to highlight are the mass flux, or the burning rate, the amount of stuff coming out of this material, the volatiles that are going to burn. The more that you have, the larger your fire is going to be. You can measure the size of our fire by flame height, which we'll call YF. And then depending on how large this flame is going to be, we're going to have a certain distribution of energy coming back in from that flame to our material to heat it. And typically from the base of the flame up to that measure of flame height, the flame is steady, so we have steady heat transfer coming into the material. Farther downstream where the flame is flickering and you're up into that thermal plume, that heat transfer decays in some way. We want to be able to describe that better. So for decades, we've had models that have tried to predict the key problem here. How fast is that flame spreading? And they looked at this problem and really simplified it to capture the key elements in the gas phase and the solid phase of the problem. So on the gas phase, we're looking at some constant value of flame heat flux over some effective distance of the flame, dividing that by some representation of what the solid is doing, so thermal inertia, ignition temperature. And this provided a good framework to try to understand what's going on in our system, but it's difficult to make good quantitative predictions from such a model because it simplifies so many things. So we're not focused on exactly what does that heat transfer look like. Is it really just a single constant value for one distance? How does that change as the flame grows? We're not looking at convection or radiation from that flame. All of the complications in the solid phase, the chemistry that's happening in there, the material properties which are dependent on composition and temperature, they're completely ignored. And any of the secondary behaviors that we see in other materials, such as dripping or sooting or char formation, all these things that will complicate behaviors can't quite put into a model like this. But it serves the foundation for what we need. As our understanding of the system gets better and our computational power grew, we were able to develop stronger and more accurate models. So in the solid phase, we went from these one-dimensional material-specific models to these multi-dimensional time-resolved solvers that can calculate material degradation based on composition and temperature resolved properties in solid phase. In our gas phase, when we're trying to describe flame heat flux, we've been able to say, well, maybe it's just not a constant size flame. We can predict flame height as a function of material burning rate or heat release rate and do a better job understanding what that heat feedback is from the flame. So that's where we're going to come in, try to do these things better. Key purpose of how we started our study was to develop a flame model that would be better than anything else that we can find in the literature. So we took really detailed measurements of flame heat feedback across the length of the flame from its base to its tip as the flame was spreading and growing, and developed a model of flame heat feedback that can predict that flame heat transfer solely as a function of material burning rate. And we'll develop it to this point later, but what I want to highlight is how the form of that model now. So from the base of the flame up from its base to some measure of flame height, we'll have steady flame heat transfer. Farther downstream, we're going to define exactly what that decay region of the flame looks like. And then using this model, we can couple our model of the flame with the solid phase solver that will calculate material degradation in response to this heat transfer, which will give us the tools to calculate the primary dynamics controlling the early stages of upward flame spread. And hopefully from there, we've generalized our model to be able to look at a wide range of different materials. Using this whole framework, we can now look at more complicated secondary behavior that we couldn't see before. So how does soot formation or dripping or charring affect this process? How does the impact of different flame retardants affect the flame behavior in the system? All of these things we can now look at based on the work that we've done. So we start way off. We build our own test apparatus to take the measurements that we need. We take a small sample, we support it inside of a steel holder, It exposes only the very front surface of the material, so a flame can spread upwards across there. We ignite it at its base by the small propane burner, which is cut off by a shield, so only this lowest region of the sample is actually preheated. All that goes underneath an exhaust hood to capture the products of pyrolysis. If we want to record sample mass loss rate throughout the test, put the entire thing on top of a balance, record that through a DAC into the computer. For a test where we're measuring flame heat flux, we're going to take a about 1 centimeter wide water-cooled Schmidt-Bolter heat flux gauge, place that at the very top of the sample, have the gauge surface flush with that of the material, measure flame heat feedback there. Everything's recorded on camera at the end. And then for materials where we need to induce flame spread, they're a little bit more difficult to ignite, we can apply a radiant panel to apply an extra external heat flux in there. So I mentioned that we're going to resolve flame heat feedback all the way across this flame. So from its base to its tip, what is this heat transfer coming in from the flame? But we've only drawn a single heat flux gauge to measure that. And ideally, I could take gauges, fill up the entire surface of a material, measure that flame simultaneously across there. But if I were to put a bunch of water-cooled thermostated gauges into the material, they would affect how the material heats up, how it's burning, that would change the spread indicator. We don't want that. If I'm going to take a gauge and place it right in the middle of the material that's going to drip or melt, that polymer melt can fall over the gauge and either destroy the gauge or at least ruin our measurements. So what we do instead is prepare samples of different heights, ignite them identically, allow the flame to spread identically across their surface. And if I measure flame heat feedback at the top of the smaller sample, effectively it would be the same as if I were measuring it at the same location in a larger sample. So we'll go through a number of tests to show that yes, the burning behavior of these smaller samples was representative of the larger ones, and then we'll put together all those measurements to get a full, well-defined model of this flame. And this required a much larger number of tests, but we were able to get good reliable data that we could work with. So in terms of the tests that we've actually conducted, we built our flame model on measurements of extruded PMMA. It's a widely used material in industry and also in standard fire tests or in labs. It's easy to ignite, it's not jarring, it's not heavily sitting. And we focused on extruded instead of cell-cast PMMA because it's much more widely used in industry. And it also presents a kind of mild to moderate melt flow. And this melting behavior is common to many materials that we want to study. So we were able to analyze its effects here and then build on that with our other materials. All of our samples were between 3 and 20 centimeters in height, and that let us get our height resolve measurements. They were each 5 centimeters wide. We chose that size because it matches the average size that we're seeing in material flammability tests. So that's about the size of the samples that we're testing there. And also in a study by Yannick Pizzo and his group, they ignited samples of different widths, 2.5, 5, 10, 15, 28 centimeters wide, ignited them all the same way, let a flame spread upwards across there. And what they found was with normalized burning rate, each of these samples was identical so long as the samples were at least 5 centimeters wide. So that lets us use these 5 centimeter wide samples, except that in the scale of the system, we're not going to see these three-dimensional effects creeping in or weird things happening at the edges. We should be safe to work with this and be able to generalize our model from there. And of course, tests that we're doing, all of them, vertical burning and upward flame spread, we're measuring mass loss rate. So igniter samples at our base, put the burner down there. We remove it once we see sustained uniform ignition of the sample across its width, let the flame freely propagate from there, and we'll measure flame heat flux or sample mass loss rate until the entire sample is involved, until we see steady state flame heat flux readings or until there's some significant melt event we need to stop early. I'm going to take a quick look at the ignition source that we use to ignite our samples. This is a side view. On the left, we have our sample holder. Down here is the base of our propane burner, a small shield used to cut it off, that flame, so it doesn't spread across the sample as we're igniting it. Here we're looking at heat feedback from our flame. I'm just going to show the final burner configuration that we use towards the very base of the sample. Nice high flame heat flux. As you go higher up, flame effectively cuts it off. So we're just preheating the lower edge of that sample to start the tests. So we can look at an actual test here. From ignition to full spread, timestamps indicate time after sample ignition. We start with a nice uniform flame across the base of the sample. It's purely laminar. As it continues to spread and more of the sample is involved, it transitions away from that purely laminar behavior. And one of the things that we should highlight is beneath the flame, between the flame and the surface of the material, we have some mild soot deposition. It doesn't appear to impede flame spread, but it effectively transforms the sample from transparent to opaque. And towards the end of the test, we mentioned a little bit earlier, there's this moderate melt flow that we're seeing, and we'll be able to characterize that in a number of ways. So we record sample mass loss rate, we repeat our test over and over again, we get a nice smooth average that we can work with from there. And then since we're breaking up all of our samples into different size heights, we want to show that the smaller ones do in fact behave similarly as the larger ones. So here we're measuring sample mass loss rate of 3 to 15 centimeter tall samples, you'll see that the measurements we've taken are all identical for each size sample height until the flame spreads all the way across the smaller samples, in which case the burning rate of that material can't keep up. It's just too small, the flame spreads from there. And so what this shows us is, yes, we can use a single burning rate to characterize the burning behavior of all of these materials. We can just measure the largest samples that we're interested in, and that can be used to describe the behavior of the smaller ones as well. So we go to our largest samples. We are now plotting measured mass loss rate versus time after when we first applied that burner. So sample preheating, nothing's really happening. Finally, we see ignition. Burning rate increases as the flame spreads across the surface. And then about 300 seconds after ignition, we saw this sharp uptick, which was related to that melt flow that we were seeing in our sample. So the sample's softening. It's beginning to drip down. That drip pool at the base of the sample is burning. We wanted to remove the effects of that drip pool that's burning because it's not feeding energy back into the sample itself. So we conduct an entire separate set of tests where we constantly remove this sample mass as it drips. We extinguish that, and then what we measure is just the mass of the sample as it's running on the wall. So that's our corrected curve here. We can fit that with a nice smooth polynomial to kind of get rid of the noise that we're seeing there, so we can work with data later. That's going to be accurate to within 3 to 5% of the actual experiment measurements throughout the test, and we can work with that as we move on. So there's our mass loss rate. Now we have our flame heat flux. Again, single test. We repeat it over and over again. We get a nice smooth average. And here we're looking at flame heat flux 7 centimeters, 7.5 centimeters from the base of the sample. And we'll see that from ignition starts fairly low. As the flame spreads towards the gauge, towards that measurement location, measured flame heat flux increases until the gauge is firmly established above the surface of the gauge itself. We see steady flame heat flux. We repeat this for every height that we're.
Could you talk about why you see steady flame heat flux?
Sure. So we have a gauge that's positioned. Can I go to a figure for this?
It's
farther back.
It's that height, right? 7.
It's at. Right. So if I'm measuring flame heat flux all the way up here, at the very beginning of the test, I'm not going to measure all that much as the flame is slowly spreading there. As it gets closer and closer and closer, at some point, the whole steady region of the flame is now above the surface of the gauge itself. So that flame heat flux is now steady. It's the peak value that we're going to see.
And the burning rate is steady too?
Burning rate is not steady, but the flame itself is now above the surface of the gauge. Is that fair?
So the burning rate is not steady, but
It can continue to increase, right? So if I'm measuring a flame that's this large, right, and I'm measuring right here for heat flux, that flame can continue to grow. Whatever I'm measuring heat flux here should be about the same.
so but the flame height will continue.
Flame height continues to increase, but I'm measuring at a fixed position. The flame has now gone beyond that position, so I'm going to see steady flaming there. Okay. We can run through that with questions later. I'll try to go through more measurements and hopefully it'll make more sense when we look at the whole use that profile. So single measurement location, flame heat flux starts low, flame spreads towards our gauge. Once it's firmly established, the gauge is steady. We repeat this test for each of the heights that we're interested in. So from 3 to 20 centimeters above the base of the flame, we do this test over and over again. We see the same behavior for each of those. Flame heat flux starts fairly low. As the flame spreads towards that measurement location, measurements steady out at some peak value. And as you'd expect, from 3 to 20 centimeters, it takes longer and longer for that steady value to be attained because it's taking longer and longer for that flame to actually reach that location. So we can smooth these out again just by fitting them with a series of third to fifth order polynomials, get rid of the noise in that data. We're still capturing the signal very well. And now we can work with these nice smooth fits based on about a year of measurements of what that flame is putting back into the sample. And so from here, we want to develop our flame model. And the first thing that we can do is try to figure out what exactly is that steady flame heat flux when the flame is firmly established over the gauge. And across the height of the sample, we see pretty much a constant value of flame heat flux on the order of 34 kilowatts per meter squared. Towards the very base of the sample where the flame is thinnest and closest to the surface of the sample, you see that measurements are a little bit higher, but we can fairly well capture that behavior with these single constant values of flame heat flux for a steady part of the flame.
Could you just dwell on that for a second and go back? So this is where the flame has extended above the top of the sample.
Yes.
So go back to the other graph.
Forward.
That one. So now all of these flames are above the top of
Exactly.
the sample. And in the bottom stage, you have the 40.
Mhm.
Uh,
Can I sketch this? Is it okay to do?
yeah,
a
yeah,
little bit?
sketch it,
Cool.
sketch it.
So,
Aside
here's our
view.
raw
What does the
material.
flame look like?
We
Do
have
a-
our
do a
flame
side
that's kind of, this is a side view, right? So here's a raw material that's burning. It's shooting whatever amount of mass out of there. Here's the height of our flame. Yeah?
But if you were to draw the flame as a sheet, would it be fair to say that up to 4 centimeters, it's laminar and pretty still, and then it starts to get wavy? Are you seeing things like
It depends on the
that?
flame that we're dealing with. I'd say it's still fairly laminar, even going up to 10, 12 centimeters. It will begin to transition beyond that.
No waves.
Not perfectly still, sure. But I guess if you're looking at that single thin sheet approximation and just the boundary layer flow, which is I guess what you're going for, right?
Well, I'm just wondering why the distinct jump.
It's a distinct jump because we're approximated just as a constant value. The individual measurements that you see there, nothing is distinct like that, right? But we can capture that behavior fairly well in a simple way for our model by approximating it with this distinct jump.
I think in the interest of time, let's.
Yeah,
let's-
yeah.
let's-
All right. So we have our steady state measurements of flame heat flux. We want to go ahead and take these measurements and convert them into spatially resolved profiles. And so we go from measurements at each individual height to what does that heat feedback look like across the surface of the sample. And here I've only showed 5 of them, but from 15 seconds after ignition all the way to full flame spread, you see more and more of the sample is being heated. And now let's just focus on a single one of these curves and try to pull out what we actually need for this model. So we have our steady state measurements of flame heat flux, although they're kind of debated, I suppose. But for our model, we're going to say from the base of the flame up to that flame height, we have steady flaming conditions, so steady heat transfer into the material. We know what that steady value is, we just showed that. Now we need to define what exactly is that flame height, how does that change as the sample is burning, and what is the shape of the decay region of the flame farther downstream. So to define that flame height, many studies that you'll see in the literature will just say, well, my flame is this tall, I see it, that's how tall it's going to be. What really matters in this system, though, is heat transfer from the flame back into the sample. So we define our flame height as the highest region of the sample, I can see on this picture, yes, as the highest region where we're measuring close to steady state flame heat flux measurements. So if measured flame heat flux is within 2.5% of its peak steady value, we say that's where our flame height is. So in words, that's written up there. And now we can plot our dependence of flame height versus sample mass loss rate for all the locations that we were looking at. And we end up with a single formulation as a function of sample mass loss rate of what our flame height is going to be. So we've now got most of our flame model done. We can go back to what we're trying to solve. We have steady state flame heat fluxes. We have a relationship for the height of our flame. Now we just need to capture what is the shape of that decay profile farther downstream. And all at once, it's a little bit difficult to see when the height of our flame is changing. So if we're plotting flame heat flux versus the absolute distance from the base of the flame, it's difficult to know exactly what that decay profile looks like. If we look at all of our measurements, it's absolutely impossible to see it on this scale. So we define a characteristic length scale for our flame, y star, but we're looking at the distance y with respect to the flame height. So am I between the base of the flame and that flame height or some region farther downstream? And if I plot my flame heat flux measurements versus this length scale, then I see that a single profile evolves for all of our measurements. So from the base of the flame all the way up to its tips for small spreading flames that are only 3 centimeters tall to 20 centimeter ones. From the base of the flame to that flame height, we see steady flaming conditions. Farther downstream, we can capture that heat transfer by this single expression, which is right down there. And so we can gather all of those equations together, and we'll see that our steady state flame heat flux is defined as a single constant value, depending on if you're above or below 5 centimeters from the base of the flame. Flame height is going to be defined by this power law expression. We have our characteristic length scale for the flame, and then heat feedback across that whole system, steady flame heat flux from the base of the flame up to that measure of flame height, and an exponentially decaying value farther downstream. Just for verification, you can see how well our model matches experimental measurements. And we see across the length of the flame at a whole bunch of different times, from ignition to full involvement, our model is actually capturing what we measured. There's no over or under prediction in the tail region. We're capturing that flame height correctly. And so across the length of the flame, the model is predicting heat flux to within about 5% of what we're measuring. So here's our flame model. We developed that. We're very happy with how accurate it is. We're now going to move forward and couple that with a solid phase solver so that we can actually predict the dynamics of material burnings in this setup. So for that, we're going to use the pyrolysis solver Thermocam. You can input initial conditions of what's our ignition source to our sample. Thermocam really simply is just going to calculate material degradation in response to this heat transfer. We can use that to figure out the mass loss rate of our sample, go through all the expressions that we just developed to figure out how large our flame is, what energy is going back into the material, and continue on with this process to see how is the material burning in response to these flaming conditions. So let's look a little closer at Thermocam. Thermocam is a computational pyrolysis solver that is used to predict the rate of gaseous volatile production of a material in response to external heat. So we represent the solid phase by a mixture of components that can interact chemically and physically. We calculate heat transfer in both dimensions through the material. We calculate the rate of gaseous fuel production by a series of first-order reaction rates. We simulate gas transfer through the material. And based on all of that, we get this key predicted quantity of what is the burning rate of our material, which we can then plug back into all the formulations we have for our flame height and determine the heat feedback back into it. So there's a framework that we're working in with this. To parameterize what's going on in the solid phase, I'll get there in a second. Let's just prepare our expressions here for how we're going to use them in Thermocam. So right now, we say that we have a constant steady-state flame heat flux into our material, but this was measured by a water-cooled heat flux gauge, which is going to be quite a bit cooler than the sample itself. So I need to know net heat transfer into the surface of a pyrolyzing material. To do that, we're going to approximate our flame as being primarily convection heat transfer. We have some measurements on the radiation convection split that I can show at the end as well. But we're going to take that steady state flame heat flux, approximate it as purely conduction, define a constant value of convective heat transfer. That H flame, we're going to define that as constant across the length of the surface of the material. And then to get this peak value of flame heat flux, we're going to say that that occurs when T flame is equal to the adiabatic flame temperature of our material.
Could you explain the justification for using convective heat transfer as the dominant heat transfer mechanism? I mean,
Sure. So we have measurements of that where we looked into how much of, in our exact system, from basic points of that, how much of the heat transfer is coming from convection radiation. I can show that at the end. I didn't want to time it up here. I think it's typically in the fire science field, typically accepted that at this scale, for small laminar flames where the flame is right against the surface of the material, you're driven by convection heat transfer in that case. It's such a thin, effectively transparent flame that radiation is not something that you're all concerned with. I guess first reference up there is what I'm going on for that. And then the second is showing how we're relating that flame temperature to what we're using for the system.
we're talking about heat flux from the flame to the polymer, not the other direction, right?
Right. So what would it be? So
I don't know. You said the flame was thin.
yes. So I'm not. So it's optically thin. I'm not worried about radiation transfer from the flame.
Okay, I didn't understand that last statement.
So depending, so at first, you can have the flame transfer energy to the material in a number of ways. Predominantly, it's either going to be by convection or radiation. Depending on the scale of your flame, typically for smaller laminar flames like we're studying here, it's treated as purely convection heat transfer.
Now that part I got. The last part, which was, since the flame is optically thin, radiation from the flame is not important.
Yes.
I didn't understand that part.
So the amount of energy that that flame is actually sending out by radiation is rather small. So I can approximate the total heat transfer from the system as being purely convection, and then that H flame is an effective coefficient that calculates the predominant heat transfer from convection and the minor effects of radiation.
I understand what you're saying. I didn't understand the last part of the logic, and that may be my issue about the issue. Just because the flame is optically thin, it means that radiation from that flame is not important. I didn't understand that logic, but let's not get hung up on that.
Okay.
You can explain that to me later.
Sure. So still preparing our model, adjusting these equations so that they'll treat everything as convection. We now adjust our steady state in the flame. Make the same correction for heat feedback across here. Flame height doesn't have to change. Characteristic scale is still the same. And now we can take a look at the solid phase of what's going into them. And for this, I need to acknowledge Jing Li, who did his PhD about a year ago with our group. And in our research group, we've developed a systematic methodology to parameterize the pyrolysis mechanism of a wide range of materials. So non-charring, charring, and composite materials, we're able to understand how we transfer through them, how these materials degrade. We do that not through optimization techniques, but through direct experimental testing. So we can understand the reactions that are occurring and the kinetics of these reactions through TGA tests. Given that knowledge, we can then determine the heats of the reactions and specific heat of each of the components that we're seeing in our material as it's degrading. And using that, we develop a degradation mechanism to determine thermoconductivity absorption coefficient. So parameterize heat transfer through that material through net scale tests. These results have been validated across a range of light scales from 0D or thermally thin heating in TGA and DSC tests up to one-dimensional heating in cone calorimeter configurations. I'm not going to go into detail on that now. Again, more backup slides at the end. But the solid phase model has been validated to predict material degradation across a range of scenarios, across a range of light scales. We can take that information directly, apply it to our model, couple it with our flame model, and see how what we can do with that. So if we accept that our solid phase is well taken care of, then we want to validate that our flame model is working correctly. And the very first thing we want to do is see, did we get that peak flame heat flux correct? So we set up an experiment where we can ignore the dynamics of flame spread. We ignite a small 4 centimeter tall sample. So within about 10 seconds after ignition, steady flaming conditions are observed across the surface of the sample. We'll go ahead and simulate this in thermocane in our model. And if we can predict that steady flame heat transfer correctly, then we should be able to match the measure of burning that we're seeing for this nice small sample. So we'll do that. We can compare measured and model predicted sample mass loss rate for these small samples. We see that they're pretty darn close. So time to ignition is well captured, the initial mass loss rate, the rate of rise in mass loss rate, all are well predicted by our model. Again, the parameterization of our solid phase was done by direct experiment. We didn't tweak any of the parameters there. We just took it directly, put it in here, applied our flame model directly as we developed it. And we got very good predictions of burning behavior. That said, it's not quite perfect. So we look at this tiny difference here and see if we can do any better with it.
But what is the jump?
The red one or the black?
The red jump.
So that's just a modeling thing. So we apply a heat flux to simulate the burner in our system.
Oh, from the burner before.
Yeah. So
Okay,
for the 1
sorry.
second where the burner is there, we ignite it spikes up. Yeah. So we want to bring that red curve down slightly if we can, because it seems to be slightly over predicting things. We go back to our experimental data to see if there's anything that explains this behavior. And we look at the flame heat flux measurements that we had for very small samples, and at 3 and 4 centimeters above the base of the sample, you see that after reaching a peak value of flame heat flux, it actually decays slightly as you go on. So we look back into our tests, and we saw that from ignition, or about 30 seconds after sample ignition to 3 minutes later, the mass flux of volatiles coming out of those small samples roughly doubles. And as a result, we see the flame sheet is stiffening and being pushed slightly farther away from the surface of the sample. So as these small samples continue heating and they're degrading at a faster rate, throwing more of this material out, it pushes the flame away slightly. It yields a slightly lower flame heat flux, as we just showed on this graph. And so to account for that, about 3 kilowatts of squared difference in measured flame heat flux, we apply a correction for this blowing effect into our model, which now gives us this flat curve in thermocane. And we're capturing our data really quite well. What
was that correction?
For the blowing effect, that as you
changed the heat transfer coefficient.
We kept the heat transfer. So exactly how we did it, we applied a additional heat flux term that so this difference in heat flux from this peak value all the way down here, we measured what that drop off would be. We removed that excess heat from our model across the same time period as we've seen here. So we applied an additional heat transfer term that removed that excess heat that's no longer coming in.
You wouldn't apply log of 1 plus B over B.
That will
So that's
blow
not the
this curve
formulation of our
away.
model at all.
Pardon?
That will blow this curve away.
Blow the curve away.
Yeah.
That's the correction, the blowing correction for the heat transfer coefficient
Yeah.
in the Spalding model.
Yeah, I know.
So we're
And-
able
and
to
anyway,
model
just-
this without using the B number at all, though. And we're kind of, that's like the formulation of our model is a key part of how we're predicting this without needing to use that. So is that okay? We can go on this? Or?
Yeah, sure.
Okay. So we include that blowing effect. We're predicting material burning behavior quite well. And we should point out that, yes, we're just looking at steady flaming conditions, but it's really important that we're getting this correct. If you go into other models in the literature, you're seeing that peak flame heat flux is reported as anywhere between 20 and 40 kilowatts per meter squared. So a full factor of 2 difference in that peak flame heat flux. With the measurements we've taken, with how we parameterize in our model, we're actually capturing material burning behavior really well. So our solid phase has been validated, our peak flame heat flux has been validated. Now we're going to move on and see if we can get the dynamics of flame spread by capturing the whole shape of that heat feedback profile. So here what we're looking at on the left-hand side is a side view of our material as it's heating up. So that's an in-depth temperature profile of our material as it's predicted in Thermocam. We see that from blue to red, it's going from about 300 to 700 degrees. On the middle figure, you're seeing a representation of flame heat flux into the material. So at first, that yellow one is just that burner that we're using for ignition. The red flame heat flux you're seeing here is a representation of the flame based on the model that we developed earlier. And all the way on the right, we're looking at measured and model predicted sample mass loss rate from that polymer. So a lot of things are going on here. In the solid phase, we have two-dimensional heat transfer that we're calculating. We're calculating the actual chemical reactions that are happening in this material, production of gaseous volatiles as they're forming, as they're being transported through the material themselves, using all that information, using that burning rate to predict the size of our flame, what exactly that heat transfer is going to be left into it. And throughout the course of our experiment, we're seeing really, really good agreement between measured and model predicted sample mass loss rate. So time to ignition is well characterized. That initial rate of burning is pretty much perfect. Rate of rise of burning is doing well, and that peak burning rate is also well captured. So for all of these submodels that we have wrapping into this flame model, there are different degrees of uncertainties in there. Despite all that, we're doing a wonderful job actually capturing this burning behavior. And we do it in simulations that are easy, computationally they're easy to perform, so they're not nearly as costly as a full CFD calculation. So we're very happy with the results of our simulation. At the same time, we see this tiny difference to see maybe we can do slightly better. So one of the things that we looked at there, again, full model results. So with and without the blowing effect, we're now doing a good job capturing our behavior. One of the things that we tried to look at was our prescription of the adiabatic flame temperature as the peak temperature of a flame in the system. Perhaps that was too high. So we reduced that flame temperature slightly by about 200 degrees to see, do we get better predictions of material burning behavior? We do lower our model predicted curve slightly. It captures experimental measurements a little bit better, but it doesn't fundamentally change the shape of this curve. So we're not set on going that route. We've tried that. A second method that we tried to account for burning behavior a little bit better is to go back to our system and recognize that in Thermocam, we're not really modeling the downward flow of this material as it's softening and dripping down. And that, as you spend all this energy to heat up this material, if it just drips down harmlessly and falls to the bottom of the sample holder without actually burning, all the energy that went into heating up that material is not actually going into increasing the burning rate of that material. So experimentally, we'll see a slower rise in sample mass loss rate because of that dripping behavior. So we applied a correction in our Thermocam simulations to add an additional mass flux term that would remove some of this material as it's heating up before it contributes to burning of material to produce that flame. We get slightly better predictions again. We're still so our model predictions are better capturing what we see experimentally, but still not perfectly characterizing that behavior, which shows the importance that we should look into how polymer momental flow affects burning behavior in the system, but we'll need a more detailed way of doing so than we apply it there. But in general, we're very happy with the predictions that we've seen here.
Could you explain though why you have that nice smooth result and then it jumps up? Like what is happening right there at that, what is it,
Right.
400 seconds or whatever that is?
So why experimentally that's happening?
Yeah, why the experiments?
So as material is heating up, it's beginning to drip down, slowly flow downwards. What we're seeing, I'd like my sketch this a little bit because it's not included here. I have stuff at the end. As you're removing some of that material from the wall and it's just falling downwards, what would be burning on the wall higher up in the sample is not burning. It's now effectively cooled because all of that hot polymer has just dripped harmlessly away for the sake of wall burning. So as you're just flowing that material downwards early on in the test, you are slowing the rate of pyrolysis front towards the top of the sample. At some point, though, the entire surface of the sample is now involved in burning. So despite that dripping from the base of the sample all the way to the top, that sample is now burning and producing flammable vapors. As as the whole sample finally takes off, then we're going to see an increased mass loss rate with the whole surface of the sample finalizing. Is that fair?
I'll accept it. I don't understand it, but couldn't follow it all.
Okay.
But go
We've got some extra
ahead.
stuff at the end, so we can show
Yeah, go
regular
ahead.
questions pictures for that. So we developed our flame model. We coupled it with thermocane to get a full model of flame spread. And now we want to move on and generalize the wall flame heat feedback model so that it can predict the behavior of a wide range of materials. In the solid phase, we already have a systematic approach to characterize non-charring, charring, and composite materials. So if we can do just as well in the flame, we have a very robust solver to predict burn behavior in this scenario. So currently, the main drawback of the model as we presented it is it only works for PMMA. So it predicts flame height purely as a function of the PMMA burning rate. In the literature, we'll often see flame height predicted as a function of heat release rate, which is directly proportional to sample mass loss rate by the heat of combustion. So we're going to attempt to scale our model expressions on the basis of the heat of combustion of the volatiles produced by each material that's burning. So indirectly, when we calculate our peak flame heat flux, we do that by calculating the adiabatic flame temperature of our material, which comes back to the heat of combustion measurements that we determined. And then for our flame height expression, we're going to scale that to go from something based on the burning rate of our material to make that a function of heat release rate that we're measuring, which we can calculate based on the material burning rate and the heat of combustion of each material that we're looking at. So we will try to get each of these measurements that we need for a wide range of materials that we'd like to consider. We looked at 7 additional polymers, cast PMMA, which would be similar to our PMMA, but it doesn't present that melting or dripping behavior. 2 heavily dripping materials, POM and polypropylene, heavily sitting materials, ABS and HIPS, and then a pair of composite materials that are glass reinforced, fiber reinforced polyester and polybutylene tetraphthalate. So wide range of different materials, they're widely used in industry that present a range of different burning behaviors, from sooting to dripping to char formation, all these things. Can our flame model capture that? How do we need to analyze it? So height of these samples, again, 3 to 15 centimeters. They're all 5 centimeters wide. And the measurements that we're going to take here, still mass loss rate and flame heat flux. And we're also going to measure heat of combustion for each of these materials as they burn in this configuration. So same test setup. We just use different materials in here. I'm going to go over the burning behavior of each material quickly so we know what we're dealing with. Cast PMMA performed quite a bit like the extruded samples that we had. So nice small laminar flame to begin with. As it spreads, we're going to transition away from purely laminar behavior. We have this mild soot deposition that still transforms the surface to black as the material is burning. But unlike our extruded samples, we don't see dripping at all, so the base of the flame is always firmly fixed to the base of our sample. We can then go to our dripping materials that will undergo a melt transition several hundred degrees below their decomposition temperature. And so for polypropylene or POM, we see as the sample continues heating, it's going to drip, the base of the flame will move downwards, and we need to be able to account for that in our model. And at the same time, POM is quite different from all of our other flames. There's no soot production as it's burning, so we get this wonderfully blue transparent flame throughout the length of the test. Towards the end of each of these tests, there is a significant melt flow event, so once we see that, we just kind of stop recording measurements, and that's how we get them.
Just curious, did you also take data on the flame heights? I know you define flame height differently, but here you have visible flame heights. And of course, there's some fluctuations. Did you take data for each of these samples?
To try to compare what we see visually to what we're seeing based on measurements of flame heat flux?
No. Just apart from this, just flame height data
We have that. So we recorded every test. So if you do want to see the heights of these flames visually, that data is
But
there.
you didn't work with any of them.
No, because the key point of our model is we're going to find flame height as a function of that heat feedback.
I understand that, but flame height in and of itself. You have some rich data there that could be processed.
It could be. And so Stas and I have talked about if we get an extra intern to help over for the summer, to have someone specifically work with that, develop a program, probably just a script in MATLAB to track that flame height visually, see how that compares to what we're getting on the basis of heat flux measurements. Is there any correlation that we can actually directly compare the two? But for right now, we have videos of it, but I haven't looked into that directly. Cool. So we have our dripping materials. On the other side of things, we have heavily sitting materials like ABS and HIPS. And like PMMA, as these flames burn, the soot from the flame deposits across the surface of the material. Only for an ABS flame, which is so incredibly sooty, that soot layer continues to grow as the material is burning. So as the material continues burning, that soot layer grows and can reach 3 to 4 millimeters thick. You end up with this dark, soft, fluffy, porous layer that won't degrade and acts as a wonderful thermal insulator. And so for both ABS and HIPS, we see that if you allow the sample to burn freely, that soot deposition actually causes extinction of the sample, even though there's quite a bit of material left behind it. So we can look at that for HIPS as well. Similar soot formation, much fancier looking structure, but in the end, the same effect. Soot deposition is going to cause auto extinction of the flame. For ABS, with the addition of an external heat flux of about 10 kilowatts per meter squared, we were able to induce flame spread across the surface of the material. For HIPS, we tried a whole number of things, from even higher heat fluxes to tilting the sample back so it hopefully doesn't deposit on it, to larger ignition sources. Couldn't get flame spread. So we basically just analyzed our data from here to the beginning on to avoid all of that messiness. But if the soot is depositing on the surface of our sample, then it's also depositing all the way across the surface of our gauge. So as the test went on, that soot layer was forming on the gauge itself too, and kind of ruining our measurements. So what we would do is repeat the same test, shield the gauge itself with a custom cut piece of insulation. So that way, as the material is burning and all that soot depositing across the surface of the sample itself, it's not getting onto the gauge. And then at various times after the sample is ignited, we can reach in there, pull off that shield, and then the gauge is able to read these nice clean measurements of what flame heat feedback would be in the absence of that soot deposition. And so these tests are incredibly tedious to perform, so it's about 5 hours of setup for maybe 10 seconds of data, but in the end, we do get decent measurements of flame heat flux, so I guess it's kind of worth it. So we have our sitting materials. We also had our glass reinforced composites, both FRP and PET. Again, nice uniform ignition at their base. Flame spreads upwards in each of them. For each of these materials, unlike the dripping ones, the base of the flame doesn't move downwards, but because of sample burnout, that flame actually moves upwards. You're left with this residual glass structure behind. So we track that as well, and we'll talk about that in a moment. So wide range of different materials that we're all studying, unique behaviors to all of them. Now we're going to try to generalize our flame model to characterize each of them.
In those photographs there, are you using the same time for photography, or those are videos, I guess, right?
These are very likely stills from videos that we've taken.
Stills
In which
from
case,
videos.
yes, we would be.
I was just wondering, because in the PMMA, it looked like you had discrete flames.
There are some times where you'll see it in another image later, we have these like choppynesses, and that's just the video of how it's being recorded, where you can almost see separate images of the flame. That's just how the camera is recorded.
You can also, you'll see waves in some of
You'll see waves.
and I've seen it in
yeah.
some of your
And it depends on which PMMA you're dealing with. We'll actually have.
very small scale.
So fair?
Yeah.
Cool. So we did a number of mass loss rate tests just to ensure that, yes, smaller samples do burn the same way as our larger ones. I'm not going to spend too much time on there. But for polypropylene and ABS, we saw similar burning behavior between all our different size samples. We can go on with the assumption, or with the actual measurement, that the largest sample that we measured, we can use the mass loss rate from that sample to characterize all of the smaller ones. Each of these curves represents an average of multiple tests that we've done for all of these materials. I need to acknowledge Kevin Korver, who completed his master's with us 6 months ago. He helped me do a number of these different tests for us. So we have our mass loss rate behavior for each of these samples. We can go on and look at flame heat flux measurements for them. In the interest of time, I'm not going to do them all separately. But for all of these materials, we measure flame heat flux at a range of different heights. We repeat those tests, we average them together. We get this wonderfully large data set of flame heat flux measurements across the length of the flame for each of these materials. And you can choose pretty much any of them. We see the same behavior that we had for PMMA. Flame heat flux starts very low as the flame spreads towards the measurement location. That flame heat flux peaks and kind of stays out as the flame is firmly established there. For our middle row of our heavily sitting materials, we can kind of zoom in on one of these. Look at ABS flame heat flux at 7 and 15 centimeters above the base of the sample. We'll see measured flame heat flux increases, it hits a peak value, and then instead of just setting it off, it actually continues to, it just decreases from there. And that's due to the soot deposition that we're seeing across the surface of the gauge. So those shielded measurements that we showed earlier, those individual data points that we have here, that's what we get out of the shielded tests. We see what would our flame heat flux be if we didn't have that soot deposition. And as a result, we can get a better idea of what that peak flame heat flux would be in the system.
Do you know why the polyoxymethylene is so much higher?
We have a guess on that. We've done a number of tests to try to figure out why, and then in about 15 slides, hopefully I can show you exactly after that. Is that fair to wait till then?
Sure.
Oh, right. But good catch, because yes, that is quite a bit higher than the other ones. So we have our mass loss rate measurements, we have our flame heat flux measurements, and before we can go on and generalize our model for all these different materials, we need to understand how movement of the base of flame affects our predictions. When we originally developed everything on our extruded PMMA flames, we implicitly included that movement of the base of the flame here, and we accurately captured flame heat flux for that material. But if the base of the flame doesn't move the same way for our different materials, then what we're predicting at different heights above the base of the sample won't be quite right. So what we did here is we looked at our coordinate system and how we defined where we are in the flame. And in our original model, we did everything with respect to y, which tells you the distance from the base of the sample. As using that system, we can say, well, our flame height is the highest region from the base of the flame where we study flame heat flux measurements. But as the test goes on, and the sample kind of drifts and slowly flows downward, we see the base of the flame moves a little bit farther downwards from where we originally started. So we want to track the movement of that base of the flame and define a new coordinate system that lets us know the effective distance where we're measuring flame heat flux with respect to the base of that flame. So that YF, that effective distance, tells us y minus the distance of the base of the flame. We're now tracking and seeing where we actually are from the bottom of that flame. And we can redefine how we look at flame height instead of with respect to where the base of the sample, where the flame started, to where the base of the flame really is. So we move that over here, and we have a new representation of what our flame height is. It's the highest part of steady flaming from the base of the flame. We go back to all of our materials. We track the movement of the base of the flame for all of them. So for every single test that we did, both mass loss rate and flame heat flux, we look at the base of the flame. We track it as it moves either downwards for different materials or upwards for composites. And with that information, we can go back to our original model and redefine how we look at our flame height from the original model where we don't account that, we don't provide any correction for movement of the base of the flame, to the final one that we're using as a generalized thing to say our flame heights are actually larger because the base of the flame is farther from where we're measuring.
Well, could you say what the base of the flame is
The
again?
base of the flame is defined here as the lowest region of the flame where the width of the flame is at least 60% as wide as the widest part. So if I have a single strand that drifts here, I'm not going to
Where's the bottom of the material?
Bottom of the material is right here, along with this white line.
Now, that's not due to dripping, that's due to,
That's
Just
due to
the
melt
expansion.
flow and the base of the flame, and that
Oh,
polymer
that's
melt
due to
moving
dripping.
downwards. Yes, and so the base of the flame moves with it. So if we go back one image, we start with everything rooted right here, slowly have dripping that goes on, the flame moves with it, and later on in the test, the base of the flame has moved slightly downwards. And so we readjust our coordinate system to track that, and then we adjust our flame model to say, now we account for that dripping. Is that okay? Cool. So we have that for our extruded PMMA. First step that we want to do is see how well it accounts for other materials when we have that dripping. We went to, we just verify, yes, we're still capturing extruded PMMA behavior well. We model capturing the experimental measurements just as well as before. And we move on and say, let's look at cast PMMA, for which we see none of that dripping behavior, but we don't need to worry about scaling by the heat of combustion because it's identical for either form of PMMA. And we see that both peak flame heat flux and the rate of rise of that flame heat flux, so across the length of this flame, our model is capturing that flame heat flux really well. And then there's maybe a 5 kilowatt per meter squared difference here, but that's well beyond the accuracy that we'll see in most models that are available. Again, even just that steady value of flame heat flux, if you go out and look at recent studies, you'll see anything from down to 20 all the way up to 40. And probably the worst I've seen was in a really fancy model where they said peak flame heat flux in U194 is like 75. So there's the big test to what exactly is that peak flame heat flux. We're capturing it really well. We've showed earlier that we validated it to predict material burning behavior. And now we've shown that our model can account for that dripping behavior for different materials.
could you say, what is the model here that you're using?
I should have some,
that thing that-
would be this. It's this collection of expressions that we were looking at before. Now using, we're just going to plug in the measured burning rate of our cast PMMA and predict flame heat flux at this height that we're looking at. Same expressions as before.
Right.
So this was good for material. We're just dealing with PMMA. As we're looking into other materials that may be more or less energetic, we wanted to scale the size of the flames and maybe that flame heat flux by the heat of combustion of each of these materials. So we set out to directly measure that by experiment. So we did a number of cone calorimeter tests in different configurations with or without without external heating, because there is some sensitivity to heat of combustion measurements in each of these configurations. The standard one that if you're running cone test on, horizontally support your sample, expose it to external heat, let it burn. We also looked at how our samples were typically burning in our test, hold them vertically, no external heating, what would that heat of combustion be, and a range of different ones in between. And then also, we went to our colleagues' recent work and then to the literature to see what would be the heat of combustion under complete combustion conditions. So we looked at MCC data, so microscale combustion calorimetry. We force our samples to complete combustion. We can measure heats of complete combustion for those materials. So we end up with a range of different heat of combustion values that vary slightly depending on the orientation, depending on the conditions that we're burning these samples in. I won't go right now into exactly why we're seeing those differences. I'm happy to do it later when we do questions. For now, it's enough to say that depending on the conditions that we're burning in, we see slight differences in these heat of combustion values. When we go ahead and try to scale our model to predict the behavior of a wide range of materials, we're going to see which of these heat of combustion measurements does the best job of doing it for us.
This is on a mass of volatile spaces.
This is heat of combustion kilograms per gram of gaseous volatile.
Gaseous fuel.
Yes.
Right.
So how does it compare to literature values?
Pretty much spot on. So if we're going to, the easiest ones to compare are the gray ones. So typical cone calorimeter configuration, we're going to be within 3 to 5% of their measurements.
So why'd you do all of these things? Just to have some fun.
Okay, so we did all of these different ones because depending on the orientation of our material, depending on the configurations of the test, they will be slightly different, which we see, right?
Why
So
would
they're
they-
slightly different.
Why would you expect them to be different?
So I was hoping to do that in questions at the end.
All right, go, keep going.
Okay. So we have all of our different measurements of heat of combustion. Let's prepare our model to try to look at burn rate for different materials. First thing we need to do is change our peak flame temperature. It's not just for PMMA, but for any material we're looking at. We're going to calculate that assuming an adiabatic flame temperature, complete combustion of the monomer to the CO2 and water, so no dissociation, using the heat of combustion of each of the measurements that we've taken there. Same deal, affect the whole profile here. And then we want to change our flame height correlation so that for more or less energetic materials, we're going to scale them by the ratio of the heat of combustion of the material that we're interested in versus the heat of combustion of PMMA, which we developed a model for to begin with. So something that is more energetic, you would expect to have a larger flame, and so we're going to scale it in this way. So we end up with 5 different approaches that we want to scale with. I'm going to walk through each of them one at a time. So we are scaling flame height by a ratio of the heats of combustions, and we're calculating flame temperature using that heat of combustion to build up the adiabatic flame temperature. So in method 1, both of those are calculated using the heat of complete combustion, so that HC total that we get from MCC tests. In method 2, we're going to scale everything using the heat of combustion value that you get in typical cone calorimeter configuration, so horizontal burning with external heat. Method 3 matches the configuration we're seeing in our normal setup, so vertical burning, no external heat. The fourth one, we want to see, can we kind of scale these heat of combustion values by 1 minus the radiant fraction of these materials? So some of the energy from these flames is just radiated away. We're looking at a purely convection-driven system. Can we adjust our heat of combustion values by that radiant fraction? And then our last one, we scale our flame height by 1 minus the radiant fraction times that cone calorimeter value. But then we recognize that towards the base of the flame, where it's well oxygenated, we're expecting complete combustion to occur, so that peak flame temperature might still go off of our heat of complete combustion from MCC tests. So on the left side, we're going to look at all of the materials that we're dealing with, and then to determine the accuracy of our model, we're looking at measured flame heat flux versus the predicted values from our model. Each of these materials, you're going to see how close we were on average throughout the length of the test across the length of the flame. And way at the bottom, you see the average predictions for all of those materials by that scaling. So a whole bunch of numbers. What ends up being the thing that we need to look at is method 1 gives us, on average, the best predictions of flame heat flux across the length of the flame for all of our materials. We're predicting that flame heat flux to within 4.2 kilowatts per meter squared across the length of the flame, which again compares to literature values where just the steady value is different by up to 20 kilowatts per meter squared. So we're very happy using that scaling.
Can you tell me, I'm sorry, how does flame height vary with Q nominally?
Nominally. So some factor.
What's unusual?
It depends on the scale of the flame. So for laminar flames, typically they'll say it's on the order of 1, although I've seen, there's a collection there, I'd say anywhere from 1 to 1.24, but 1 is typically accepted. For turbulent flames, it's generally and more consistently accepted as 2/3. But usually for each of these studies, they're looking at steady burning or a single type of material only in 1 or 2 of the regimes. In about 4 slides, we'll look at comparing how exactly our model fits compared to these and see what that looks like.
And what is N in your model?
For ours, it is going to be 0.452, I think. I'll show it in a moment. It'll all make sense. The picture will be there. It'll be okay. It'll be there. It'll just, you gotta get there. So it's, I mean, it's like 4 slides, and you'll see how it's all working. So we're happy with our accuracy of our model. We're even happier that we happen to get it from heat of combustion values that we contain from milligram samples that we use in the MCC. So if you're trying to design new materials and you want to see how that flame's going to behave, you can do these milligram scale tests and hopefully get some information out of that without having to make a full 10-gram sample.
Just before you leave that, I think you should really take a look at POM, because that's a flame that's probably burning at its highest temperature with very little radiation.
We're going to look into that in like 4 slides.
Yeah, I mean, so, okay.
So we accept that this is our scaling method. We look at how our model predicts the flame heat fluxes for all of these different materials. In the steady region of the flame, in the tail region where the flame is still rising, we're spreading across the sample. We see really good agreement for pretty much every material across the length of the flame. So we're very happy with that until we get up to POM, where, again, as you pointed out, those experimentally measured flame heat fluxes are quite a bit higher than we're predicting from our model. So we tried a number of things to try to see why that is. So very, very first order, we can just kind of say, well, what would happen if we change our peak flame heat flux value, raise it to match exactly what the experimental values were? And if we shift everything up in that way, we'll capture steady state flame heat fluxes really well, but the tail region of the flame, so that rise would have been well over predicted by our model. So it's not just a function of changing the peak flame heat flux, but there's something different in the structure of the flame itself here. So we looked into trying to understand differences just on the basis of that flame temperature. So we calculated flame temperatures for each of these materials. Even if we're seeing perfectly complete combustion for POM, some loss of efficiency because of the soot formation in the other flames, just the peak temperature of the flame was not enough to describe this behavior. One of the clear things that stands out, POM is way different than all the other flames that we're looking at. We see dripping behavior, some other squiggliness in the flames, but if you had to pick one that was different from all the others, it would be POM. And so what we're seeing in this flame is unlike all the others. It's burning completely. There's no soot formation. And so if you imagine rotating everything to the side, that soot is going to form on the fuel-rich side of our flame. So between the surface of the sample and that flame sheet itself, for any of these wonderful yellow flames, you're going to have soot forming there, and you're going to have energy being radiated out from that soot to the outside world. And so for each of these yellow flames, you effectively have this heat sink near the surface of the material that's slightly fuller than you, because of that radiation out there. For POM, where you don't have that behavior at all, because there's no soot forming to send that energy away, the temperature of that flame right near the surface of the material might be slightly hotter than you would see for all of these other yellow flames, which is possibly why the peak flame heat flux for POM was so much hotter than all the others that we had. So we tried taking high-resolution images of our flames from the side, trying to see is there a difference in flame standoff distance there. There was nothing conclusive. We then looked to surrogate fuels. We prepared a series of wicks, which we soaked with a couple liquid fuels. We burned in the vertical configuration with either methanol, ethanol, or heptane. The first two of which are pretty much transparent, not all that sooting at all. Heptane, which gives us a nice sooty flame. And 7 centimeters from the base of the sample, measuring flame heat flux the same way as we did in these measurements. Where the transparent, non-sooting flames, we see flame heat fluxes that are about 10 kilowatts meters squared higher than we had for our typical yellow sooting flame, which matches fairly closely the difference that we're seeing in our POM measurements from what we're predicting. So that was the series of tests that we tried to look at why exactly is that flame heat flux so different. it would be wonderful to have highly resolved measurements of that temperature gradient in the flame for fueling flames, and see if we can get more out of that. But we're working in that direction. For all of the other materials, we're capturing things really well. For POM, at the very least, we're still capturing that flame height curve. We just need to understand what's going on with heat transfer from that flame. So we have our generalized model of the flame. We get right here, which we wanted to look at just before on the top of what n is equal to. And we can compare our flame height expression to others that we see in the literature and how it compares to our relationship with heat release rate. And for the most part, the shape of these curves are pretty much the same. So we have a different exponent, but we're seeing similar behavior as flame height depends on heat release rate. We're very happy that we've been able to obtain measurements of really small flames right down to ignition so that all of these values of flame height go beyond what we could capture in the literature. So small flames, we can predict that behavior well. And to explain the difference of why ours are significantly lower, we should look at how we're defining flame height. This has come up before, whether we should look at flame height as a function of flame heat flux or just the highest part of the flame that we actually see. So if we go to our tests, we can say for this sample, at this time in the test, flame height as we define it by a measure of flame heat flux is about 12 centimeters. If we just look at where are the tips of this flame, that's quite a bit higher than that. So depending on your metric to say where your flame height is, you might have very different predictions of what that flame height is actually going to be. For our test, we've used flame heat flux as that critical value, which is really what is controlling the behavior of the system. Or pretty much, actually for everyone else in the system, they just looked at the flame and said it was this tall, and we believe that that's what's causing most of the discrepancy that we see here. So there's that. So we have our flame model. We can now use this whole setup to try to branch out and apply it to predict the behavior of other systems. So one member of our group, Chad Lyman, who just defended his master's, looked into seeing how can we use the framework of this model to predict material behavior in the full-scale room corner test. So going from the 20 centimeter tall samples that we've looked at to 2.5 meter tall samples where you ignite them with a 40 kilowatt burner, how well can we predict that behavior following the approach that we've used here? This is a full 200-page thesis, so I'm going to narrow it down to like 30 seconds. But performed a whole bunch of experiments, used the framework for our model, we tried to predict that thermochin, and actually saw pretty good agreement in terms of initial mass loss rate of our samples, and really importantly, the rate of rise of sample mass loss rate as the flame spread across these very large wall panels. So from the large scale back to the small scale that we're interested in, we'd like to move into seeing how well we can model the U194 tests. It's one of the most widely used tests.
Just to go back, are you using your heat flux model for
We're using
these
the same
ISO 9705 tests?
Yes, so we're using the same equations for it. The empirical parameters that go into that were adjusted to account for the fact that we have different entrainment conditions. So we're looking at a room corner instead of an open wall, and we're going to fully turbulent 2 meter tall flames instead of small laminar ones. So
you're extending your model into this turbulent range?
And we can look at, so Chad has an amazing amount of data on that. We can go into all of that and just kind of showing that it can be extended that way here.
But then you have a square burner in the corner too.
Yes.
And how do you define flame height here?
Again, by a critical value of the heat flux. I think this was.
So he's measuring the heat flux in these
Yeah,
huge.
so if you look at, you can see these
Okay.
tiny little spots there. You went through and measured through, followed the same approach that we did, so how to use a model to capture that behavior.
You know there's a thesis in the department that measured all those heat fluxes.
That's Chad. He did just that.
No, before.
Also possible.
Not possible. It was measured point-wise through for the room corner test.
Was it published?
Yes, it's in this report, and it's probably published in the literature. It's by Scott Dillon.
We must have referenced that.
Yeah, you would reference that. We looked at these measurements. We looked at all these measurements, and now this matched the data that new data that could update for the heat flux.
I'm going to try to wrap this up real quick because I know everyone wants to leave. So let's go do that. We're going to move into U194. It's a very widely used standard test method to assess vulnerabilities of these materials. It's a natural extension of our work. It's not the same scale. We are looking into approximating our samples as a two-dimensional object, applying the same paralysis model for what's happening in the solid phase, and using our model of the flame on either side of the sample to define flame conditions here. The one thing that's kind of holding us up right now is what we're going to use to define the heat transfer from the burner used for emission of these samples. I know there's, actually both of you measured that in a recent paper 5 years ago. There's 2 other tests that came out more recently. Wide discrepancy of what they're reporting for burner from heat flux. We have a student helping us now to measure that, and we should be pretty close to trying.
Depends how you hold the flame to this.
It's on a lot of that, yeah. So Lindsay's helping with that, and we'll try to do a good job of modeling it ourselves as well. So that's our extension for U194. Using the framework of this model, we're also able to understand how exactly gas-phase flame retardants are affecting flammability in the system. So within the expressions that we have and with the measurements that we can take, we can look at how flame height, heat flux, and flame stability are each affected by the presence or absence of these flame retardants. What we're going to look at here is measure flame heat flux from PBT samples with increasing concentrations of a brominated flame retardant. And we're just going to look at that peak flame heat flux. We'll see that for each of these materials, regardless of the concentration of flame retardant that we had in there, we weren't affecting that peak flame heat flux, which is something that no one's been able to really show before. So that's one of the things that we're looking at. We're going to try to look at flame stability by seeing critical mass fluxes at ignition and extinction, and move forward into our last extension. In addition to all the models that we ran in Thermocon and all the tests that we've run, we did a series of FDS simulations, performed at 3 different MES resolutions, finding, of course, one, to see what data do you really need to predict flame heat flux in the system, to predict flame spread in the system, how does that compare to what we're doing in our model? So we had a couple of reaction mechanisms, so simple single step, which FDS normally use, finite rate kinetics, and then where we're pulling these material properties from. And in the interest of time, we're going to kind of quickly go through this data. We do get mass loss rate measurements from FDS. We can see that in 3 of our samples, we're actually able to obtain ignition. Each of these, depending on the resolution, so let's say for 60 seconds of simulation time on our coarse resolution, that takes about 2 weeks. For our medium one, that's taking about 2 months. For our fine one, I got about 15 seconds of data after 4 months, compared to, I reran this test 2 nights ago in Thermocon, and it was done in about 2 hours. So we can compare the burning rates, we can compare the heat release rates of each of these samples. You can see that even at the medium and then definitely at the coarse resolutions in FDS, we're starting to see some numerical errors creeping into our calculations here. But what we can still pull out from this data is what is the flame heat flux predicted in FDS versus what we're getting in Thermocon 2D. And at each of the resolutions, we're actually seeing pretty good agreement between net flame heat flux from the flame in the system in either of the 2 models. The biggest difference being probably an order of magnitude, or 2 orders of magnitude reduction in computational costs of using our system versus FDS and all of these flames. So just a different light, we're looking at some of the data. So I'll move forward with that. Comparing burning rates, we did our best to try to compare burning rates of these small samples after ignition. Weeks or months of data from FDS, and that's the very best that we could do. A couple hours of everything to predict the whole picture. So we're moving that direction. When I'm over at NIST, I'll have access to more powerful machines, and hopefully we can look at this a little bit more in depth. So this is just our last example of an application of how we're using our modeling framework. So key outcomes, we were able to obtain highly resolved measurements of flame to surface heat feedback at the critical length scale for flame spreads, really detailed measurements of flame heat flux that just weren't there before. From that, we developed a flame model that can relate heat feedback just as a function of material burning rate. We moved on to couple that with a solid phase solver so that we can predict the primary controlling dynamics of flame spread at this scale. It bridges a range of different scales from the TGA tests to the bench scale tests that we developed our all that to all the way up to the full scale tests that Chad was able to do for flame spread. And finally, we generalized that model to describe the behavior of a wide range of wall flames. We're very accurately predicting those measurements of flame heat flux to a whole bunch of different materials across a range of scales. And moving forward, we're going into a bunch of different applications of our work. So that's all I have. It's finally over. I know this is long. I left this blank because I don't want to write down individual names and miss any of them. So
You're gonna ignore everybody.
well, no, I'm going to go through them personally now. So there's the obvious ones of Rich and the FAA who's funded me for like 3.5 years. That pretty much made this possible. And you were also interested in following through this work, so that was really great. Thank you for that. We have to recognize BASF and Roman Kramer out there, who's been funding us recently and doing some of that flame retardant work. I think ASME, SFE, and the University of Maryland gave me different research and teaching fellowships, so that was kind of cool. And SAS, obviously, like, this is not at all possible without your help. And every one of your students knows how much better it is to be here because you're helping us do this work. You are incredibly dedicated and wonderfully hardworking, and it's made this entire process.
Let me
way
just
better.
sign it.
But I get to finally say that after 5 years of working here, it's made so many things better. So
I also signed for Jim.
so we have, I should thank the faculty and staff in this department. I've been here for 10 years now. I've gotten to work with each of you, and that's been really great. Our lab group is magically special. We're clearly the best lab group in this department. So I know but thank you for making this just a better trip through for the last years. There's a number of students who have worked with me, probably a dozen different interns who have made this work possible. Some who've done their own masters with this work, and that was really great. Family and friends, you still exist. You're at the end there. I know I'm never home. I'm always here doing this, but you're still being there. And I think I covered almost everyone. So now we're done. And you can all just leave.
Well, as per standard protocol, we're going to entertain the questions from the audience. Once it's done, the audience will leave, and then we'll get together with the committee. Isaac, please direct the discussion on the right back. Go ahead.
I just would like to give a comment on Professor Zachariah question about the thickness of the flame. So my understanding is if your flame is obliquely thin, what you can neglect is absorption part in the radiation, but you still have to take into account the emission of the flame. And after you talk about radon fraction, you talk about soot. So all relate to emission. Right. So to have an argument if you can neglect or not radiation, I think you need an extra explanation.
So I can go to slides on that wherever they might be. Not quite this one, but we did look into directly measuring the radiative convective components. Here we go. Flame heat flux in the system. And so you talk about absorption, you can kind of reflect that. At the same time, the effective emissivity of a very thin optically flame is going to be pretty low. So what if it's vacuum straight up? So what we did in a series of experiments was try to measure just the radiative component of our flame, assume the rest was convection, and based on that measurement, see what the fraction of heat transfer came from radiation versus convection in the system. Is that fair?
Yeah.
So we did a series of tests where we recessed our gauge back into the sample, as we've shown here, and then by doing so, you can reduce the convective heat transfer into our sample because if the flow is just not passing directly over that gauge. And then by recessing that gauge, we can try to approximate a measurement as being purely radiation and see how that compares to the fraction of total heat flux coming into there. Is that okay? So I think the next one will show. So the gauge is recessed. We have some view factor that accounts for how much of the total radiation circle we get here. There's video of that happening, how we actually measure what that recessed value is going to be. But what we also saw when the gauge was recessed, there was this minor component of convection still getting there. You could see deposits on the gauge forming. So we went through some work to develop an effective view factor for convection. We're going to accept that. So what fraction of convection goes to the recessed gauge versus what's at the surface? We can compare our measurements to what we recorded at the back at different recession gaps to see what's just radiation, what's just convection. I'm going through this super quick, but I just want this one picture. With this one graph.
But do you have the percentage of?
Yes, I do, and it's just not. So these are here. The percentages themselves were on a table that we're not going to see, but we can zoom in on the actual fractions that we're getting. At the very end of the day, at the scale that we're looking at, with a reasonable approximation where the error bars should be here, the radiation fraction that we're seeing from these flames at these different heights are all less than 20%. So primarily convection in the system.
So it's not a radiant fraction though, right? We all the same.
No, this is just the fraction of flame heat flux
Okay,
coming.
so
through.
that's it's a radiation fraction that gets on the wall, but it's not a radiant fraction.
So there's more work to be done here. It was in one of the ongoing work things. If I'd like to take more detailed measures of this for a range of materials, I think I can do it carefully. For the most part, though, at the system, flame heat transfer to the surface by radiation is pretty low. So you can approximate this purely convection as long as you're getting the total amount of heat transfer in there correctly. You'll do a decent job here, like heat flux. So okay.
Unless you have your blue flame.
Unless you have that one, but that we think is a structural difference.
Okay. So it's not a question of radiation. That's what you mean.
We think that all of the others are effectively cooled in some way by radiation that we're not seeing for this one blue flame. Yes. But fortunately, there's only one material that behaves that way.
Thanks.
So about the experimental data from PMMA, where you see how it slows a little bit and then it speeds
Yes.
up. So I understand the initial concept of why it's slowing down.
Mhm.
So it slows down because you're dripping and you're losing mass, and so that depresses the growth rate of
Right.
mass loss. But then why does it have that point of inflection where it then speeds up to much faster than the model predicted?
So there's a mess there. Some of that is just experimental issues of as it's dripping along the base of the holder and you're spreading out to a large region of the sample that's burning. There's about 2 centimeters below the base of the sample, and that's just insulation. Another 4 centimeters below that, that's just the steel holder that's holding it. So you have this larger area of the sample that can suddenly start burning. So you have a sample there that is burning that we don't see in our model. Is that okay where that's coming from?
Yeah, I think
So
an accumulation of stuff.
if this is our sample front view, at some point, eventually, we also have this extra area that is burning that we just don't have in our model, right? Because we've had stuff that's dripped down there. And at the same time, what was slowing us for so long was this part of the sample was never really burning because as it heated up, it just slowed down. That stayed nice and cool. But towards the end of the test, the entire surface of the sample is pyrolyzing. So we see that uptick as that part is also finally burning too.
So I understand the uptick when that's burning, but I don't understand why the slope changes. Like it makes it seem almost like it's a piecewise thing, where it's that whole part isn't burning at all, and then suddenly it's starting.
It's not a direct hit, but there is a gradual.
Okay. And that might be just a simplification.
Is it possible that as you have the dripping come down, these are little rivulets, and they're closer to the flame, to the global flame, so as a consequence, they're going to burn faster?
The small streams of what starts dripping down here.
Yeah, if you draw a side view and you draw a flame sheet.
So as that drips, so let's make that sample on this insulation. I think it's fair to say that
Yeah,
a
no.
much thinner flame.
No, as the drip comes from the top, it comes down, and now that drip is closer to that flame. So
yes and no,
so
we're
it-
also seeing this is not really there. That's burnt away, right? So there's the dynamics of that process are complicated to say exactly. Is it closer or farther? Is the flame
Does it
itself
regress that much?
Towards the end of the test, depending on the size of the sample, there's nothing left. It's entirely burnt out. So it could
What's the
regress up to
thickness of your
a
sample?
quarter inch.
Quarter of an inch?
Yep.
Oh,
So it depends on the test, depends on how long you let it burn.
so- Yeah, because that could, and is it insulated in the back?
It's insulated at the back throughout the majority of, so it's really only for the very smallest of our samples where we see that full burnout. For most of the others, especially for our larger samples, it's difficult to say exactly where that front edge is there. We see bubbling and swelling of the material just because it's heating up. So define exactly where that front surface is there's not a straightforward answer to that.
If you look at and you together the Markov stress curve that is purely modeled without any dripping at all, you do have a non-linearity on that curve, right?
Yeah.
So it's not
there is an
linear.
uptick in that.
So the physics of this flame is fundamentally curved, right? Because and that's associated with the fact that as the burning the pyrolysis zone gets larger, the flame gets larger. And so you should expect a general non-linearity in this curve. Now the question is of the degree of this non-linearity, and that can be argued about But even without any effects of flow, you're going to have a nonlinear behavior, and it should be there. It's a part of the dynamics of that system.
Follow-up question to your answer. Does that recession, does that significantly increase the surface area of the sample? And is that accounted for? No, it's not very much.
It's not. To increase the surface area by recession, no. And throughout the majority of the tests, the fact that it's even moving, for most of these tests by the end, the base of the gauge at the top there is flush with the top front surface of that sample. So it's not a major effect, but it also varies strongly depending on the size of the sample and how long you're going to the test. So it's much more later stages where we start seeing things here, but mostly okay. We all just want to go.
Anybody else? All right, then thank you very much for coming. We appreciate it. Grab some food on the way out. Feel free to help yourself. There is this vegetables, it's very nice.
That's all I got. You just wanted to take the best
Then if I just want to do
Get
Yeah. So I had this orange crown and that got called up. So that I could put it on the thing. Very hard. My hands are shaking the whole time, so it was a mess. Chili pepper.
Oh, is it?
Yeah, you can if you want, but
Is it real?
just a warning.
What kind of pepper is it?
A hot one.
Okay.
we are missing Dr. Brook, but I think we can.
He'll be back. He just stepped out to the restaurant.
I'm sure. Mike, would like to start? We're going clockwise.
I'm not familiar with this. The FBS,
Fire dynamics simulator.
but it did pretty well, right?
It did, but it took forever.
It is a
So it is a 15 minutes of fully resolved computational dynamic solver. It's very powerful. It has a solid phase regulation mechanism that's similar to what we're implementing. So we use the same reaction mechanism there for the solid phase. The difference is how it's defining that plane itself. So we don't do fluid dynamic simulations in thermic. In our model, we use this empirical.
I'm just amazed that it works so well. You say it takes a long time.
Yes.
Sounded like it took a very short amount of time.
So for a thermican, we can knock these out in a couple of hours.
No.
For FBS, it's weeks.
Yeah, but it took you 2 years to take the data. If this simulator really works.
Okay, so one thing I should also point out, for our simulator to work, the first 80 seconds of just preheating,
Yeah.
which I can kind of highlight over here, we don't even simulate that at FBS. We preheat the sample in thermican because we've shown good time for ignition. We measure the temperature gradient across the surface of the material. We say this first 80 seconds, we go to the thermican here.
Well, I understand it's not really part of your dissertation. I'm just conceptually trying to understand how one of these things is that good for something this complicated. So, okay.
But he said it's fully resolved. Does that mean it's a DNS?
So we did DNS simulations there.
That's what that is.
That's what that was.
Yeah, so there's no heat transfer coefficient in the wall. You just
No, so it's just by
QTDF.
well, the attempt was to, I mean, whether it's fully resolved or not is the question that we try to answer, right? So we
Right, and the last
we
one
started
is
with something that didn't look fully resolved, and then we reduced scale, and on a smaller scale, we only were able to make about 15 seconds of that simulation. So that's, I mean, I think the jury is still out. We have to get more data before we can say that it's fully resolved, but it's a DNS. Right? So there's no submodels of any kind, neither on the boundary nor.
But it gets the chemistry, the heat release right. That's the hard part.
Well, that's very simple.
Define it.
Yeah, no, there is one reaction there, okay?
The
It
hard
says
part is getting the heat.
fuel and air meet, they instantaneously react, and they produce the energy according to the heat of combustion. It's produced in a single element. So there is no full chemistry there.
Right, so I went through that real
You do
quick.
it with full
Um,
chemistry, it will take you years.
What I can do actually with full chemistry is, that is our orange curve here, with single step reaction in the gas phase, trying to get that to heat up. And sorry, it's the binary reaction is our purple one. So single state reaction mechanism where we take Arrhenius reaction properties from, whose paper was that? Was it Foreman? 40 years ago?
Yes,
Well, Cal,
yes.
Cal,
Well,
yeah,
it's-
Seshadri.
Yeah,
Was
Shadri
there-
and Williams, so his name was on that one too.
Yeah.
Yeah, so we take the reaction mechanism that they proposed. They had one and then a correction for it a year or so later, which are different in their A&E by several orders of magnitude.
But this reaction mechanism is a single reaction.
Single
Yeah,
reaction.
it's a reduced.
And if we try to apply that here, we do have burning rate, which is just like mass loss. So the sample is degrading as it's heating from the burner. We never actually
That was
can
just
see the purple curve here.
It's the -4.
We never get ignition in
Doesn't
that sample.
it doesn't only ignite that kinetic.
So if we try to do a detailed description of that chemistry, we're kind of missing it. Each of these other simulations, what we're using instead is this really simple reaction model where we can calculate the rate of that degradation in the solid phase, and if you have enough of that gaseous volatile mixing with your air, it mixes that together in cell and says if that reacted and it got over a temperature, some threshold temperature or flame, then we say yes, there is a flame. So it's just presence. Is there enough in my fuel? You don't even worry about the reaction rates. Just if there's enough there, it will burn.
It's a standard eddy dissipation model.
In this model, there's soot formation and radiation.
There is radial fraction, there's a
Yeah.
shadow wall, is it?
Yeah. So it's kind of going empirically measuring what that radiation would be and directly plugging it back into it. It's not.
Now, one of your colleagues has a very nice tool for measuring temperature, pyrometry.
No, just talking about Dr. Sunderland.
Yeah.
Okay.
Have you tried to use that method to estimate the temperature here and see whether that's reasonable relative to what your model would tell you?
Of what and where? Is the peak temperature that we're defining for our flame?
I don't know, wherever you want to. But
I
peak
want-
height, for example, the flame height, when you're defining a flame height, you know, what's the temperature there relative to what you think it should be? I'm just curious whether, you know,
I think.
are you learning something about the fundamentals of the combustion process, or do you have a very nice way of fitting the experimental results and using scaling arguments? And that's very powerful. Using scaling arguments like I can scale by the heat of combustion, et cetera.
So you're asking what our end result of our measurements were?
Well,
or
so
can
can you-
get more out of that?
Well, no, that's not what I was asking. I wanted to know whether you can use this, whether the fundamentals that you extract out of this can be used in a higher level model. And can you use that to predict things like flame temperature? Do you think it wouldn't work?
We can compare, so if we do directly measure those temperatures, we can compare what our model is predicting as a temperature to see how well that's doing. In terms of actually having measured the temperature directly, I don't have that. But we do have, so we have experimental measurements of flame heat flux. So if we do have a model that more accurately calculates the chemistry and the temperature there, we can compare what is that, some say the estimation doing in terms of its prediction temperatures and predicting the flame itself. If it's getting heat fluxes correctly, we'll see it because we have those measurements. And then because our measurements and our empirical representation of the flame match each other, we can compare the flame temperatures predicted in our model to direct temperature measurements that we take. We don't have that data though.
How complete is the combustion of these kinds of materials?
I don't think it is.
It's not, so we have how would you want to define combustion efficiency first?
I think
That's
CO2 to water.
CO2.
And going all the way to CO2 and water, or comparing like the theoretical
Heat of
Heat of combustion.
We have measurements, so we do have that. We have measurements of CO to CO2 production for each of our fuels in the code calorimeter, which I think are in, I'm pretty sure are in the paper, but I didn't show here. And we also can compare the combustion efficiency if we'll define the heat of combustion in any of the rotations we're looking at versus a standard combustion efficiency. So either complete combustion in the microscale calorimeter or versus the standard calorimeter setup. So I'd say for everything except, I'm pretty sure I wrote it up in there, so if I'm off on the numbers by a little bit, it should be corrected. I think combustion efficiency as defined by, let's look at, so if we're going to compare the heat of combustion that we're measuring in any of the burning configurations, which are fairly similar, the gray, red, and blue curves, to heat of complete combustion that we're getting in the MCC, those are on the order of 90% for each of the materials that we're looking at.
I really want to define what MCC is.
Sorry, microscale combustion calorimeter. It's you're able to pyrolyze a milligram scale sample in an environment. So you flood it in a nitrogen chamber, you expose it to a linear heating rate, so it degrades, and you carry the volatiles that are produced there in towards a high temperature furnace at about 900 degrees K. Mix it with
Isaac, it's 900 C. You made that mistake in your thesis. I corrected it. It's 900 C.
Okay.
It's actually 1,000 C, but whatever.
Okay.
But you're saying that the combustion is almost 90% complete?
Off of, if we're going to look
From
at
the gases.
the gases,
The gas,
we're not
yeah,
so
because
we were
there could
looking at
be
combustion
char
for gas
left
volatiles.
behind. And this is heat of combustion per unit mass of gases.
Oh, for
involved.
unit mass of gas, okay, got it.
Yeah, sorry for
So you don't
passed slide
know,
quickly.
you don't really have a number for,
We don't, so for our measurements, we don't have any measurement of char yield or anything like that, because we have a lot of just sample that hasn't burned yet left over by the end of the test.
Yeah.
We do have,
There's
depending on-
full information from the phone data.
we have them, yeah.
We have that whole materials and stuff like that, separate stuff.
all right, well, you have to leave, right?
Yeah, I gotta leave in a few minutes.
Don't you?
I just, my thing was, coming back what Jim was picking up on, when you were doing this change in the boundary condition, you kind of just flippantly referred to it in the text, and there's no like details of exactly how you're applying that second term. And
Second term being, I'm just trying
for
to.
the boundary, the heat flow boundary condition to get the correction for blowback.
This guy, right?
Yeah.
So would you like me to explicitly define?
Yeah, I think it'd be good to just put in
Sure.
exactly how
That's
you
fair.
applied that second term.
I can
so that
sketch it out here.
Because I
so that
wouldn't
we're
be
all-
able to reproduce what you did based on what you said.
In the appendix, I'm going to include the actual simulation, so it is fairly.
Oh,
clear.
you're going to include all
Yeah,
the
it's just-
simulations?
yeah. It's
Okay.
the input code
Then
is
you
fairly
might just
short
put
there.
down that you can look at the appendix. then.
Yeah. If you do that.
Aren't there
Which is
standard
good, but I'll sketch it
procedures?
so we know exactly what we're doing.
For the second term.
But
we
it's
have to
basically
have-
this, right? So if there's.
Right, but are you just like taking the measurements and applying it?
Yeah, and
empirically?
so what our model will effectively do is say.
So
once
you're just
things are-
forcing it into there.
Exactly.
I see.
So we have
I see.
what we're predicting, what we're actually seeing,
I
so I
see.
take this difference.
So you're doing a measurement of that and applying that to the
applying it.
model.
So I apply basically this negative heat flux to remove that same amount.
So you just apply what you measure, but does that scale to different fuels?
Well, that's for the
We can, I'd have to look at the lower heights of some of our smaller samples to see if it does. And I don't want to give an answer right now and say, yes, it does or it doesn't.
Yeah, it's a very subtle effect.
It's-
3 kilowatts,
Right.
right, out of.
So it's a minor one. We could ignore it and we'd still be doing, I think, better than any other model of spread out there.
No, I think it's okay to do what you're doing. I just, like I said, it's just important for the
More
reader to
specific,
understand exactly
That's fair.
how it's being done, so that they could reproduce it if they needed to.
That's fair.
They'd have to make these measurements in order to reproduce it right now. So that's fine. They just need to know how to do that.
Okay.
I think, that's done a lot, so.
Let me just follow that. Okay? Because there are standard techniques in the literature for heat and mass transfer where you correct for the blowing. And even in combustion, there's a term that shows up that corrects for the blowing. If you look at Spaulding's works, you'll see what he's done.
Right.
So why not do that?
Within the framework of our model, that would add yet another parameter that we don't really want to include. And within what we
Well,
have.
the parameter that you would include is the mass flux.
When we're calculating mass flux from the first principles, Jim, you suggested that we scrap it all off and instead assume a steady state burning rate. Well, this burning rate is
No,
steady
that
state.
you could reduce that
not
instantaneous
steady.
burning rate by the factor of blowing or something like
Right.
that.
but that factor
Which is a
of blowing
3%.
What
50%.
is it, the
If we do
Sherwood
that,
number and mass
then
transfer?
then it drops down and we have awful
So it's
predictions.
completely,
It's like off the charts.
so that probably should be in the thesis as a mention that doesn't work. Because that
Well,
maybe
I
that
thought
only
everybody
works
knows
for
that.
the
I can't
steady
believe,
case.
how
But
could
it-
something fundamental not work? I mean, that's fundamental.
It's not fundamental. It's based on very simplistic assumptions that
No,
that's
it's
all
not.
that steady state model. Yes, V over
No,
V1 is
there's a whole ton of literature on heat and mass transfer, and people have done mass transfer problems exactly in laminar conditions, and then look at the heat transfer.
but the V over V1 is not an exact solution of climate problem. It's not even
It's
close
not
to
an
exact.
it's only, that
It's
only shows up in a stagnant layer model.
Exactly.
Yes, but in the other words, there's a whole wealth of literature on heat and mass transfer and the correction for blowing.
We calculated this thing from the first principles, right? So we actually,
They have first principles in their approach.
I don't know, Jim, you have to be a little more specific. I mean, how exactly do you want us to do that? I mean,
There are solutions for heat transfer with no blowing and heat transfer with blowing.
Which solution are you referring to?
I mean, you have to look in the literature. I could show you books. All right, so maybe that's.
You go back to your.
I mean, we are arguing over 3 kilowatts, right? That's
No,
our
it's not.
measurement shows that the blowing effect is 3 kilowatts. It's outside of the range of our uncertainties. That's what this measurement shows. Okay, they show that this blowing is really inconsequential for this measurement. Now, either our measurements are fundamentally not correct.
No, I think you're tailoring your results to measurements. And you're ignoring some techniques that could apply and enrich your analysis.
How am I telling you the results to the measurements?
Or by just subtracting that off.
But show in the curve without the subtraction.
Actually, he's supposed to be answering.
Yes.
But yes, I guess. Could you show the curve before the subtraction? Sure. Okay, so show me, please. I mean, this is the prediction, okay? Without taking into account the blowing effect at all. Okay, there is nothing there about the blowing effect. You're saying it's a poor prediction?
No, I'm not
I
saying.
think-
Okay, show me a
didn't say
single
that.
result in the
Stas,
literature.
I didn't say that. I think the analysis.
Okay, so this is not tailored to anything, okay? There's no blowing effect here at all, right?
No, but you used your measured heat fluxes to get your correlation.
Yes, I do. So do others.
So you're going in a circle.
But we're not directly applying at this time, this is what our flame heat
All right,
flux is.
here's what I would say. There's a classic work in the literature by Ahmed and Faith, and they solved the laminar problem and the turbulent problem.
And we did this thing, and it's off by 50% here.
Well, I think you should put something in the thesis, a sentence or two that says,
That's right.
because when you read this little blowing effect thing in your thesis, I spent 15 minutes looking through the thing where you just described how you did the blowing effect correction, and I couldn't find it.
Right.
And I expected it to be some Spaulding V number thing, and you said we did this, logarithm, blah, blah, blah. But I didn't see anything in there about it. So I think Jim's right. I think if it's a fundamental concept in combustion, that you should at least address it and say why you didn't use it. The other thing is, when you did your blowing correction, I thought it was as bad in the negative direction as that is in the positive direction. And I wasn't sure why you even bothered to do it. It under predicts to the same extent the other one over
It's
predicts.
overlapping.
I don't think so. It's about the same. I wouldn't even bother with it, really. Like you said, it's close enough the first time.
I like it because it represents an actual behavior that we're seeing in our experiments, that our model would otherwise be missing.
Yeah, but I think you should, if you're gonna go that way, I think you should justify it on a theoretical
That's
basis
fair.
first before you dismiss that.
That's
And then maybe make it some fraction of the mass loss rate use that as your blowing effect, some fraction of your computed mass loss rate or something. You know, that's just basically your blowing
It
effect.
cannot be a fraction of the mass loss rate because the whole model is coupled in such a way that this condensed phase part of the model is designed to give you response to the heat flux. You can mess with your heat flux, it's completely empirical, but you cannot mess with your mass loss rate predictions because they are consequence of 20 different
You
factors.
can discount the
I mean, that would be,
heat transfer coefficient by some fraction.
you can do that.
Yeah,
That's
whatever,
right.
whatever.
But that's what he did.
Well, he didn't say that. I don't know if he did that. How would I know that?
Write it out.
But that's exactly what he did.
Okay.
But by the fact that you went to a heat transfer coefficient model, why did you just use the heat flux
Because the heat flux being
correlations that
measured-
you got? Why did you have to go to,
Because that was heat flux to a water cooled gauge, which is going to be quite a bit higher than we're seeing.
but then you could
Samples.
correct that for the surface temperature of the material?
It would get rid of re-radiation out of there, but I would need some way to affect that if I'm looking at, if it's purely convection. it would be N minus T6.
Yeah, I mean, we do that in our measurements, and we have a way to correct for that. So we can take our results to the real material.
I think we are correcting for this, but I'm missing why you don't like the correction and what's different between them.
Well, you have your heat flux measurement, right? And that's there. Why go to this framework when you could work directly with that heat flux?
If I took that heat flux directly, I would still need some additional correction to say, well, now the surface on the material is a different temperature.
Right.
So are you upset with this choice of how we're correcting for it then? Because
Well,
I have to do something.
I think you're putting yourself on a path that is not necessary. I mean, overall, I think your measurements are really great. I think the scope of the work you did is great. But if I were looking at this, I would look at the Ahmed and Faith framework solutions for laminar and turbulent flow. And they have a framework of theory. They're solving the equations with the turbulence model. And they have results that they predict to, albeit steady state. But if you're going to apply it to unsteady state, the gas phase is fast enough so you could use that gas phase solution in an unsteady model.
They don't predict anything about the plume. It's all steady and under the plane. The whole spread is
No,
dictated by the plume.
they have heat flux beyond the plane, or whatever it is. I forget what's. I haven't seen it in a long time. They have results beyond the plane.
But these results are off by a factor of 2 from what we measured.
Yeah, well, you got to look at the scales too. And
What
what
do you mean?
they did is they tripped the boundary layer for the turbulent flow. So you got laminar and turbulent flow, and you have an experiment that has an obstruction at the beginning that puts some turbulence into the whole process.
So, Jim, explain to me, if I take their model, if I calculate the heat flux, it's going to be off by factor of 2. I will not be able to predict my burning rate here. How do you expect me to reconcile those things?
Because just as you've done here, there's parameters that have to be put in their model, like the radiation fraction.
So you're suggesting that I take their model and randomly scale
What
it?
I'm saying is that their model, basically,
We just talk around it.
their model is
Here's
in a sense fundamental because they're solving an exact solution for laminar flow. Let's just look at the laminar flow model. It's an exact solution for laminar flow. They did it numerically, and they did it analytically. So why wouldn't that apply?
So, okay, so let's say I apply that.
Well,
and I
first of
go
all,
and I make that adjustment. Here I'm looking at a peak heat flux of 35 kilowatts per meter squared. I apply a correction of 3 kilowatts, so like a 10% correction. If I try that approach and I'm off by a factor of 2, so by a 5 times difference in the change I'm seeing here, I'm way off in the burning rates that I'm predicting here, right? So I can do that. I can try their approach. I can say, here's what happens if we do that. Here's how our flame heat flux would change. Here's how much difference.
Yeah, but
we're gonna
you have to match their ideal solution to your experiment. As I said, in their solution, they have laminar,
Mhm.
so, and they have some data for the laminar region. And they do show the effect of blowing, clearly, in their results. And then when they went to the turbulent region, they put a trip, so the whole thing was turbulent. Now, you have something there that does some kind of tripping, and it disturbs this to some extent. So if I look at your flames, I say they're quasi-laminar. They start off laminar and they start to move around, toward they're in that transition region. So, in laminar case, you would get a higher heat flux than in the turbulent case for pure convection. So I would say your higher values are due to that you're more
And that kind of
laminar.
goes into what we're seeing just while doing measurements. It's easier to show that way. But, that kind of comes into why we're seeing slightly higher heat.
In the laminar zone, you should have very high heat fluxes. Really high heat fluxes. Right at the leading edge, you should have heat fluxes much higher
But you
than
don't go
that.
to
So let's say, perhaps, if I go all the way down to the very basic,
Right,
then that might be
right.
there. But if I go ahead and plug in 70 kilowatts per meter squared, which is what Kataragi says, the peak you're going to see at the very, very leading edge there. And if I try to apply
Why
that
was it
to
his upward measurements?
yes.
Okay.
Interferometry.
Well,
No,
I mean,
not
vertical
downward,
burning.
not downward.
It has a downward and upward. Yes.
You gotta look at upward measurements.
Yes.
Yeah.
And so we're consistent.
His upward
So-
measurements, I don't think are 70.
No, those are 28.
Yeah. Yeah.
And so we're consistent with that. When we apply the exact fractions that we show, here's how we treat this as convection, and we go from the steady flame heat fluxes that we're seeing to the
Again,
cold gauge.
what's the length of his sample and,
Very
I
similar
wanna
to ours.
say within,
what is it?
Factor
You have a
two.
range.
I want to say that he's going to be from this range downward, 10, 12 centimeters.
I think you only did it once.
Right, one size sample, so it's
Yeah.
like 10 centimeters or smaller where we'd have
Right,
those.
right, so, and then the question is does he trip the boundary layer or not?
I don't know.
I mean, because
I don't think I should.
that's, it. You have those issues facing you here, and that's all.
At the base of the flame, this flame is laminar, right? There is no question about it. And it gives you 40 kilowatts per meter square. We do not resolve the edge of the flame. The whole thing starts at
No,
4
I
centimeters.
know. I wonder why 5 centimeters is that key.
I don't want to say, so we show a sharp jump just because we have a simple model to do it.
It's just.
We could
it's
provide a
kind
curve
of
to do that,
the
right?
whole
So
way.
we could do a nice smooth curve and that would be more consistent with reality because nothing looks like that in.
Well,
right?
but yes, but
But
that's from my point. If you apply theory to this, which comes from a model such as they have,
Right.
and you say it's ideally pure laminar heat flux, you would get a distribution. And even if their results was not correct for PMMA, then you would say, all right, why isn't it correct? And it could be not correct because they don't include radiation. Now you put a radiation fraction in their B number and you reduce the results.
And now we're adding so we have a single input parameter here for burning. Now we're adding a number of things we have to measure experimentally, plug in.
Well,
tweak, so we get it
radiation
correct.
fraction is a key parameter for all of these materials.
But is it necessarily the same with how it's been measured at the different scales and the different orientations?
I think it would.
Here.
I think it would definitely affect heat flux. If you say radiation fraction doesn't affect heat flux, I
I mean,
can't think
so
of it.
we
Well,
looked at that, right?
So,
We
so,
did
so
our-
full CFD model, do you agree that full CFD model at DNS accounts for all of these factors?
Not if they just put a radiation fraction.
Not the radiation.
That's exactly what you want me to do, right?
No, yeah, because you're doing something analytically.
So let me,
If they do it in a CFD model, that's cheating.
like, no, it's not. That's how it's done in the state of
It's
the art.
cheating. It's cheating.
But if you put the radiation, if you measure the radiant fraction in a full simulation with radiant fraction that you and Rich measured, you put it in, you get near zero heat flux to the surface from radiation. It's all convection. even based on the.
Well,
on the
it's a
So you're
series.
saying this, I'm sorry,
It's a
you're saying
trade-off.
the step is due to a
There's
transition
some
from laminar to
radiation,
turbulent?
but,
No,
but not,
what I did.
the
I'm not saying, so I
radiation is
approximated as this step.
small, it's
It
like
could be done
less than
smoother. We
5.
did models where it had it nice and smooth, it made no difference for our final predictions. What I'm saying is towards the base of the plane,
I'm telling you, the
see if
radiation
I have a
pattern
video for that.
is very small
no idea.
to the wall. I'm saying,
I don't think you could say that for the yellow flames.
well, I'm saying you can't, because if you do a detailed model
So-
far beyond unmatched phase,
What I'm saying is
and
just
you put
towards the
radiant
very
fraction at the
lower
measure
part of the
this one,
sample,
you get
flames
very
are a little
little
bit closer
to
to
the
the
wall.
surface of the
But the
material.
FS
That's why I'd expect like
did a
plus
lot of
one
work
higher
on
there.
wall flames.
And so
Yes, but it's a
if
turbulent
I
flame,
look at all the
thick one.
measurements that I had, which were, you know, not discrete, but some amount
Yeah,
of
it's
noise
not.
here, I can reasonably well approximate
What,
it.
how much
Just
radiation
as
do
a
you
set.
measure?
And
It's,
I think
peaks
it's
at like
related to
5
that plate
kilowatts
standoff
per meter
distance. Pictures from the
That
side
is a
don't
score
quite do it.
like-
For a
What really
10
matters is that
centimeter
it's
tall
radiant
limit.
right at the wall.
So
But I do see
Peak-
it slightly
radiation
higher
peaks
towards
at
the
about
base. I see that the
5
flame is slightly
kilowatts per meter
closer.
squared
And
for
I
a
can reasonably approximate it this way.
Yeah.
You're
or
right.
about 10 centimeters, but theirs gets
That
higher.
we have a
Ours-
set, it's
ours
purely
is
for
between
purposes of
5 and 7,
planning
right?
this model.
For
It reduces the actual
I would
parameters.
really like to see someone measuring it with a ray radiometer or
Mhm.
with
This
a-
is what we did.
So
We created our own ray radiometer, basically. Like,
Looking
just like
at-
John DeRees did, yeah, basically, that's what we've done.
Okay,
It's between 5 and 7 and 10%.
did he show that data?
I did as a bonus at the very end, so I can take a look at that now, just so that we know. So that was what Sebastian was asking about, and I zipped through it really, really quickly.
Bend phase convective models should work really well.
It sucks. In a major way. It's
no,
completely
no.
screwed.
I've not
No.
used Faith's models on these, but I mean, we used Kim, DeRis, and Crosser, and
It's the
Emmons,
same.
and they work fairly well.
There is, but for Jerry has a much more complete model.
There is more, but
And he
there's some
solved
ambiguity
it.
to the terms.
He solved the exact equations for the laminar case. So there's
Mhm.
no, there is only solved the approximate equation.
These were
Right.
tests that we did.
Yeah.
Faith did they numerically
They
integrated
did
those
the
equations.
numerically, so they have it
Oh, there's your
dead on.
All right, so here's what we did to effectively create a radiometer. We have a gauge that's recessed into the back of the sample and shielded it with a piece of insulation so nothing gets
Yeah,
deposited
but
on there.
you see, you're measuring there, that thing is inside, right? So between the flame and that, there's, you've got stagnant layer and a moving stuff.
Mhm.
So there's some conduction.
There is some non-radiation heat transfer for
Yeah,
that.
there's
And we
non-radi-
went through a series of corrections to find out how can we represent the, and I wish I had the table, I'm pretty sure I have the table in here,
Well, what I'm
actually.
saying is, why don't you look on the other side of the flame? Because if you say radiation from these thin flames
Mhm.
should go this way and this way
But they're not
almost
going to be
equally.
the same. Because I
It's a
have
thin
these high molecular weight products of decomposition that are going to block some of that as well, right? So what I'm measuring out here on
Not
this
in
side.
this thin. I mean, you could estimate that from the recent work that was done by, what's his name?
But I have, why
I
go
think
to
it's too
other
thin.
measurements and then estimate a correction to that when I have direct measurements of our system?
I'm saying it's a difficult measurement to make.
This was a pain to do.
Yeah.
Um,
And there's other heat transfer going on there. Yeah, so.
And so there's a
factored
short
that out.
section in there, and I want to say section 2, probably 2.5, that goes into how we did this, how we corrected for exactly what you're talking about. And I don't have error bars in this figure, but it should show you the uncertainty of that correction, how that propagates to the final certainty in our radiation fraction. We can show, you're right, if we don't make corrections for non-radiation heat transfer, we get numbers that just don't make sense. And so
One last point though. You have to admit that you put your gauge straddling the point where you have go from blowing to no blowing.
Mhm.
And that's where the heat flux drops, goes up.
I mean, at the top of the sample,
Yeah, yeah.
I repeated those measurements when it was directly inside of the sample too. So
Yeah,
we have some here. I did the exact same thing where I put the gauge right down the really made a taller sample and kept the gauge in the same place. ways, no difference in measurements.
But then how do you explain the blowing in flames? I mean, if you put your gauge in the sample, wouldn't there be blowing there?
Well-
And above, there would be no blowing?
Yes, but if I have blowing here, right, and it pushes
Right.
my flame out,
Right.
it's not going to immediately jump right back.
It does.
So from the
The
side
data
view,
from FAIT
I
show
have
that.
my flame here, and then it just kind of jumps right back in. I can hopefully look at some side images of samples where we have that. Where would that be?
I mean, they
I
have
don't see
detailed
that.
data that shows that.
Listen, I'm trying to understand, that according to our data, the
Right.
whole blowing effect is 3 kilowatts on 40 kilowatt measurement.
But
With
it
uncertainty
depends-
of
it
plus
depends-
minus
It
5.
depends on the mass flux.
No, it's the highest one we observed throughout all our measurements. I mean, it's just high, I mean, it's the highest one. That's all we see. We might be missing something in our measurements, but our measurements do not show a strong blowing effect.
I think you did an excellent job in taking the data and finding things that fit your data. But I go back to what Mike said. You ignored some fundamental approaches.
Is that what Mark said?
Well, I was trying to get to that. He had articulated better because a lot of these models, as far as I could tell, are just basically an ad hoc way of getting a representation of what you observed experimentally. For example, like scaling with delta H. Now, the reason it made sense to me after you said Q to the N, where N is close to 1, okay, well, now I understand why the delta H scaling works.
And there's a theoretical basis for that.
Otherwise,
Just
there's
to
no
see where it
reason to
fits
say
into-
it should scale with delta H. It
You're
could
right.
scale with delta H to the 14th power, right?
You're right.
There's
Okay,
no
so
reason
the
to
way I
believe
use
anything
that, I
should be
could've done-
linear.
Right.
Why is this thing linear? PMDT, why is it linear with
Because, just, that's pretty much standard. And so when I introduced that,
correct,
maybe.
that's right.
Yeah,
Right.
so I had that expression, I may not have done it as cleanly as I should have, so there.
Well, anyway, that was what was missing for me, was the physical and relating what you observed to the physical interpretations that have come in the past, where generalized formulations have been made, where you write down the general equations of heat and mass transfer.
Right.
And then you use scaling arguments to throw terms out and say, here are the dominant terms. I didn't see the relationship here with that kind of analysis that's gone on.
Okay.
That was my point.
So it comes through in here, and we do that direct scaling on the basis of the heat of combustion by saying, I want our flame height to be a function of that heat release rate. To get it from our mass loss rate measurements, and I need to include that heat of combustion, right? And so that's where that direct scaling would come from. So if I just did this for PMMA, didn't worry about any other materials, I could just easily replace this with Q if I measure the heat of combustion or measure the heat release rate directly. So the only difference, A and B would change, but that's.
Well, there's no reason why should go with DMDT to some power 1, right? Or is there?
I think
That's my point. This
So there's no
equation
reason why
here, there's
flame
no
height should
reason.
scale with mass loss
There's
rate?
nothing fundamental about this equation. It's just an equation you use. Say, okay, I have some data, I need to fit it.
Yeah.
I'll start with
on
that
the
equation.
right, that a cubed prime to the n, there's a fundamental. We scale that. You get n is 4/3 for laminar and n is 2/3 for turbulent. But
So there, I mean, I can go to half a dozen studies in either direction that say it's just going to be, it is a function of these two, or it is a function of the pyrolysis height, or however you're doing it.
You know it is. Of course
And
it
that's
is.
where it
I
comes
mean,
from.
that's not really the point that I was trying to make, which is okay. I mean, yes, you know it is, because your graph showed you it is. All
And
right,
there is
so
a
now you take that graph and say, okay, I'm going to model it some way, and you're going to model it this way. Or you could say, okay, if I start with the general fundamental equations for heat and mass transfer, can I represent that curve in this way?
It does give me that. And so early on, and I may have just not done a good job presenting that here, but there's, a dozen studies in the intro that show you where this is coming from, how they develop this expression.
And maybe just that I'm not familiar with the literature, so, it's not really my
there is
area.
some debate on what this is. And Michael brought up whether it's 4/3 or 2/3, and there's arguments over whether I'm just supporting my sample out here, if there's a lip that is sent below it, if there's a wall, how does that affect that parameter, all these different tweaks for it. In the end, and I'll have to get to the end there, but when you do compare pretty much all the models that are out there, and when they list it as a function of our heat release rate, they can use 2/3 is generally accepted. It's through theory you develop that for turbulent flames. From experimental measurements, you'll see that there as well. In the laminar region, there's, I'd say, still debate on what exactly it should be. And if we take our measurements and kind of fit across that whole range, we're still capturing that behavior. If I just took our larger flames, let's say, purely fit through there, I actually get like 0.65 as my exponent. So I'm spot on with that as well. But trying to fit through all of there, I can still represent it with the expressions we have here. And then if we go up to Chad's work that he did, he presented a month or two ago, we looked at purely turbulent flames. You see same expression, same formulation that we have here, just shifted to the right for larger flames.
But are you looking for some theoretical justification of existence of that expression? Is that what you think is missing? I mean, the exact form of this expression is not something people know, but people do not have a theoretical argument that suggests that such expression exists.
Yeah, I guess I was looking for something like that.
I mean, there's a plume theory where people relate the height of the plume.
Yeah.
So that's sort of, and again, and basically what's done from that point on is people play with those coefficients by trying to fit it in their experimental data.
No, they did. Some people did when they plotted a lot of data, but other people got the 2/3, and I don't know what the thing is for laminar, but they got a coefficient for the laminar.
Well, 2/3 in laminar coefficient then gets tweaked by the coefficient in front that comes from the measurements. There is no purely theoretical expression for this thing anyway.
Well, no, you can have just a physical scaling law approach, right? You can either just do dimensional analysis or from the simplified
Well, that's
momentum
where
equation.
there's
come
all
up.
this expression for
Plumes.
plumes. But even the exact solution for plumes, they don't get corrected. Like so when
Still an A.
all this Makapri and Zukorski stuff, they didn't tweak it for the measurements, right? I mean, they first derived theoretical solutions that were highly simplified. They said, then let's introduce this extra parameters and do that, and make sure that it matches the actual measurements for the range of fuels. This is how it's always done, basically, and that's just
not for the 2/5 column.
you're still fitting the exponential factor there.
So the 1.02 that goes in front of that.
That 1.02, that's a fit.
That's what we're talking about.
That is totally a fit.
That's what-
But if you look at the work that Brian Grove did for me, we show that you don't need to do that. You can apply theoretical principles to this, and you'll get something like 1.02.
How do you measure plane height?
We take the late data in literature.
How did they measure plane height?
Typically, people measure it average by eye or average by video.
Well, that means that it will not match our results.
Pardon?
Means that it will not match our results.
No, I know. You're defining flame height based on heat flux.
Exactly.
Yeah.
So you're absolutely theoretically.
So you can't compare it to people that measure it by eye.
That I don't understand, because you're saying it's a completely theoretical relationship. Why is it then should be not one-to-one? If you're saying you don't use anything to derive.
No. There's no good results for predicting the intermittent thing. People only do it on average. That's because they don't solve the unsteady equation.
So the point is, people have a general understanding that it's dependent on heat release rate, and after that they fit, their experimental data. And what we've
Some
done
people
here is
do,
not.
but other people keep it like it should be. Like if you look at McCaffrey's results for temperature and plume, he keeps the theoretical result for his far plume temperature data. But then when you get near the flame, things change because of intermittency. So some people do and some people don't. If you look at what Hosemi does, he tends to try to keep it. But there are, and if you look at the exact solutions for these cases, you know, you can derive results based on the fundamental equations that govern it. I mean, there's no, if you're denying those equations, then.
Well, I'm denying that there is a single solution to the literature where you predict burning rate as a formula spread outwards correctly. Anyway, show me like the NDT versus time, the actual prediction of the flame development on the surface, which is predicted correctly for laminar flame.
No,
or any single sample.
You have done that. You have done that here. There's
Right.
No
So I'm
question
saying
about
I'm questioning the following. I'm questioning that if every you implying that what is here is known theoretically, and it's a simple matter of applying this model to be able to predict it. I'm asking you to point me to one result where it has been exercised, where you actually predicted the burning rate as a function of time for unsteady spreading flame like this. Anywhere, ever. I mean, show me a single work. Well, I mean, just point me to the book.
I mean, the only work I can think of is work that I did a long time ago on the ISO room corner test.
Okay, well,
And
this is not ISO room, but let's compare.
that gives reasonable results, but I wouldn't say it's perfect model.
In this result, you use theoretical relationship by unmatched faith.
No, but I've used it in other cases. I mean, I
Well,
wouldn't
okay,
deny.
show me
I
the
wouldn't-
case where you did that prediction.
I wouldn't deny. I wouldn't
No,
deny their
Jim,
work
show
as
me,
a framework
please.
for.
Maybe we should
Yeah,
continue
we
this
should stop,
discussion
yeah,
so we
yeah.
can
Yeah,
we can not let Isaac keep
I
swimming
mean,
here.
no, what I don't like is the fact that you're saying, well, there are things that you can use, but when it comes to actually using that, it's really not possible to do. Okay?
All right, I'll accept that.
I have one question about the PMMA data when you were deviated and then accelerated.
Yes.
But those mass loss rates, I assume, are ones that you're actually measuring. That's a global mass loss rate of the entire sample, is that correct? And that you're measuring in a balance?
Yes.
This thing sitting in a balance and you're measuring the mass loss rate. And that's what you're plotting versus time. Right. So if this thing's dripping, are the drips landing on the balance also?
Right, so they would, and they do, because it's just the holders.
Okay, so maybe the depressed part is the drips falling off and not burning, and then the pool fire igniting and the.
So if we go back to, and that we had earlier in our measurements. So this is the difference between the blue curve letting those drips burn as a pool on there, and the black curve removing those drips, extinguishing them, and not having that extra burning rate count towards the burning rate of what we measure on the wall or on the holder itself. So I could just pull those drips off as they fall, and if they're not burning in the pool, then there's no additional mass loss from there. So if I actually go ahead and look at the signal, so what I'll get from my balance is that, right? So if I'm just looking at versus time. So when I have that dripping behavior, if I let that drip pool exist and burn, then I'll get something that kind of looks like that, right? And that would give us our higher peak. What I did instead is I would keep continuously removing these, and I would get, as I remove them, I get these discrete jumps of that stuff there. But since I'm just looking at that burning rate, I can take those measurements of what's just burning on the wall. And we've got at least 6 tests in each of these 2 curves, so that the little times when I'm using data by pulling stuff out there, it's going to cancel out just by not always using exactly the same time.
Oh, the other thing I wrote in the thesis is, you're using the heat combustion for polyoxymethylene that you use on 14 and the MCC is dependent on that 13.1 average value, right, of course. And but POM's an outlier in that correlation. So the real heat of combustion, if you look at our paper on the bomb calorimeter measurements for POM, it's about 16.
Okay.
So that's going to put you in the right direction. I don't think that's going to solve your whole POM problem.
Helps. So
Yeah.
so I'm pretty sure we're actually referencing one of your MCC papers for these values.
You are, but those are incorrect because they're
Okay.
they're based on 13.1
Okay.
kilojoules per gram.
And so the newer one, because this was 2011 or 2013, that correction where you point that out, you point in the direction of what I can just reference and say, no, for this one, I'm going to use this different value because.
No, the thing is with POM, you've got to use the bomb calorimeter. The actual heat of formation calculation you do for PMMA.
Okay.
If you did that for POM, you'd get 16.
Okay.
Okay. When you use oxygen consumption, it carries so much oxygen with it that you're not getting the right value.
Okay.
That E number is really about 14.5 for POM.
Okay. So then bomb calorimeter experience, if you have, I can just type that with your name.
Yeah,
So,
you've got the reference. It's 101. The heat of combustion.
You wrote that at the very end. I saw that one.
Yeah, right.
Yeah,
So
okay.
use just reference that paper and use 16 for POM and redo the calculation. I mean, it'll get you a little bit in the right direction. But
Yeah.
it's going to solve your problem.
No, we looked at tweaking our temp. So it'll scale our flame height a little bit, which we're actually doing okay. We get the time when it's getting to peak, all right. We looked at different temperatures and assuming that same coefficient, heat transfer coefficient of H, and 200-degree differences in temperature, which I don't expect to see just from going 14 to 16, don't bring us all the way up there.
Yeah.
They'll bring us slightly closer.
Yeah, there's some radiation issues in there that would argue more, but whatever. I'm not sure that's the difference here.
Well, radiation issues.
From soot and stuff, I mean, you're kind of, I don't know how you're dealing with that efficiently, but that's probably the answer that you're looking for.
We think so in the framework that we kind of presented it in. Yeah. That radiation kind of cools the flame nearest the sample, but does not move on.
So you think that the radiant flux is high from the flame? Is that?
I don't know, maybe, I mean, it's blue, maybe CO2 really.
Oh, then you mean it's low, right? Because it's blue, not high.
Well, it's yeah,
Because there's no soot.
right. So, I don't know. I don't know how it goes, but I'm sure that's the difference in this thing, and I don't know if we just started doing it.
Okay.
Have you ever stuck a thermocouple in there?
Once, wholly unsuccessfully, got coated in. It was a quick thing. Can I just try to get something? They're a mess. If we want to do it, we should do it, carefully. And so.
Because you're getting the same things for ethanol and methanol.
Right.
So there's something going on that we don't understand about these luminous flames.
Well, he has a theory for that.
I can sketch that out. I might be able to do a better job describing it now. So I kind of came up on that when I showed it, but maybe it wasn't clear then what I was going for.
What's your theory?
And so we looked at a number of different things, but if we have this as our wall material and some flame that exists there, for any of the yellow flames that we're dealing with, somewhere in this region we have soot formation, right? And that's where all the energy is being radiated away. It's not a huge fraction of the energy of these flames, right? There's still primarily convection dominated, there's not much loss there, but this radiation loss is going to drop the temperature of the flame right there, right? So if I were looking at a temperature gradient near the wall without that radiation kind of heat sink there, I may see some kind of profile. With that, I would expect more of a drop in that temperature.
What are you using for the surface temperature of POM when you do the heat transfer?
Well, it's calculated on the fly.
So it's based on the
It's not a fixed temperature. It's defined by the decomposition, by the SC, by all of this.
So what is it approximately?
700 degrees.
For
Okay.
what? For PMMA.
Okay, sorry.
It's
For
not,
PMMA, but on the up in the
it's
order.
not that high. It's
Well, that's gonna
about,
be-
it's about 250 C. I'm telling you, that might be the difference right there. It's not that high.
So
That stuff is a gas at 400, there's no question about it. C.
Okay, but when we're comparing
I mean,
these heat fluxes, we're not actually using the surface, we're not doing net heat flux. The comparison we're showing is total heat flux to the gauge. So the.
No, you're subtracting your flame temperature from your
No,
surface
no,
temperature.
no, what I-
this measurements,
no,
no, this
no, no, no.
measurements are for the cold gauge.
So
No,
what
your
we
heat
present
flux
here is for, so that we have
Oh,
a,
I see, this is your POM heat
Yeah.
flux measurements.
Yeah.
Right, okay.
I mean, POM and the whole model, I mean, there's no, I mean, it's not really, I mean, there's an in-depth variation in this model. Things like that.
so I'm not showing net heat flux, but what I applied is QHFG, so the heat flux gauge, heat flux that you were taking.
Isaac, could you write an expression for the heat flux from the flame to the wall by including a term for convection and radiation? Could you write that on the board?
Are you asking just for like the really basic of
The
that, or within the framework of our?
No, I mean, write it out based on physics. What would be, and let's take the basis, flame temperature to the wall. And H is the convective coefficient with or without blowing, with blowing, obviously.
Sure.
Okay.
So then we need some effective emissivity for our flame. And then- Is that what you're asking for?
Right,
Okay.
right. And then if you look at an expression for the flame temperature that you would get from a diffusion flame,
Okay.
it would drop due to radiation fraction,
Yes.
right? So as your radiation fraction goes up, your emissivity would go up.
Yes.
So I think that starts to explain qualitatively what's going on
Where?
in all of your cases,
Which case?
in all of it.
Well,
But this is
what do you
gonna
know
be-
what's going on?
Low, even for hits, that's fairly low.
Well, I think that when you get to the methanol and the polyoxymethylene, that is very low. Now, even that could have some radiation from the combustion products, but it's low. It's lower, obviously, than the luminous ones. So I would say that polyoxymethylene fits more of the perfect convection model. And then the others are lower because of that.
Because
There
of,
you go.
because of what? Because of the
Because
second
your,
term?
your
This
flame
guy
temperature
drops
drops.
down,
You,
right? So
you
you're
drop,
saying
you
this
drop.
drops.
Oh, we did that, right?
We looked
did
at
that
that, so that-
exactly. It doesn't fit the data. We did that
So if
scaling.
we, I mean, we're looking at a difference of, 15
Yeah.
kilowatts a meter squared. I can drop that temperature by 400
Yeah.
degrees and keep it as it's not.
We thought about that. I mean, that's
But
method
if you
number.
have a laminar flame,
Mhm.
there are solutions for, let's say, a wall burning. So let's forget about Emmons problem, a surface burning, and then there's a flame temperature there. Now, if you say that that radiates because of a radiation fraction, you drop the temperature that he
We drop
calculates.
it by a couple hundred degrees. We can look at Michael's measurements or Jay's measurements, see what those peak ones are. And I dropped it even beyond that temperature to see, can I force my heat flux to get all the way down to what we're seeing based on that? And it's not just a peak temperature difference. Structurally,
No, but you got those things trading off because as radiation goes up, the temperature goes down, but the radiation term starts to go up. So you have two things interplaying there.
right, so, but if I look just for POM, where I don't have to worry about that, and I'm only focused on this part, and then I adjust my temperatures in that same way, and I don't have to worry about trade-off, I don't have to guess what my acidity is. I just scale my temperatures in that approach and see if I can get that. I'm not getting there. And
I'm just saying PMOM could be your base for pure convection.
it Could be, but it'd be for one material of which no other material behaves in the same way.
No, but then you extend from that.
Arguably, yes, but if we extend from PMMA and it matches all the other materials that we've done really well, here's our exception, adding a correction for everything so that it fits the
It's
exception.
just a different point.
So in
of view.
future
I
work,
totally
you should
understand
take a
what
look
that's
at
the
this.
baseline. Unfortunately, but it just adds another
Yeah,
layer.
right. I'm gonna have to go and try.
Right.
I think we.
I think-
I
was-
think you've
No, I
suffered
think
enough.
we've yeah.
I don't know.
Thank you very much.
Oh, I think you're right.
Yes. You'll come back.
So I think you did a really fantastic job at putting all of this together. I do have questions, as you've heard, but I think he's done a fantastic job. I'm certainly willing to sign off on this thing. And I'll give him my comments tomorrow, but I have to run.
Where are you from? Or some of these? Where's he gonna go after this?
He is going
To
to
have a drink.
Oh, he's going to this.
If I was him, that's what I would do. I'd be drinking and stuff instead of burning.
Yeah, it's too bad about the pie experiment. I don't know if I should, I don't know if you can pass them based on the failure of that experiment.
Oh, sorry. Didn't he insult you, Rick?
Yeah, I think he did.
Wow,
Be nice here.
How did you solve your group?
Well, he just said your group was better than everybody else's group.
That's it.
But I have to admit, we don't have a dragon on the wall. So
I hope he finishes the picture before. Should be in there, because that's a nice picture.
All right, gentlemen.
All right.
All right.
Thank you very much for coming.
All right.
All right.
Ciao.
I did some really great work.
You want to fill out these things? or-
Oh, you just fill out one.
Where did you? So, yeah.
See you, Rich.
But I do think you should go back to the temperature measurements on the POM. That would be interesting.
Yeah, well, the idea that he has here is that basically explained in this term, radiation distorts H. That's what we say. Okay, that's basically our hypothesis for this thing. The presence of the soot layer distorts H effectively. It makes the H smaller. Now, you're right. The temperature measurement will be good, except we're just afraid that when you stick it in the soot layer, we're going to have all kinds of issues. That's my only.
That is something you need to do.
That's my only issue. So I'm afraid that we end up with this measurements with more questions. That we
There's another way you can do it too.